All right, that's good. Oh, and it's recorded, right? Okay. Is it correct? This one is okay. It's okay now? Okay. Cool. So okay. All right. آره مردم خواهم ساعت جنس اینجا کدام
Okay, welcome to the last day of Cosmo. So, sorry. Yes, Cosmo 23, that's true. So, we will have some plenary sessions this morning, and then that will be followed by part sessions. So, we'll start the first session. The first speaker is Arman Shafilu from Korea. And Arman is going to talk about the statistics in cosmology in general. And I think that's it. So please.
Okay, so thank you very much. First of all, thanks the organizers, Juan Garcia, for establishing such a nice cosmology group in Madrid. I mean, this is really great, and having many friends and colleagues from old days that now they are all well established. I'm very happy to be here, and thanks for the invitation. So yeah, so my talk would be a combination of many, bits and pieces. That's why it would be like a plate of tapas, which I try to introduce some problems and some issues which we have in general with the data analysis in the context of physical cosmology, and I hope that it would be interesting and useful for many audience, mainly for the young people. So you will be bombarded by lots of information. I'm not going to details of most of the topics, but I hope that it can, open a page. And if you are interested, literature is everywhere, and then one can discuss about them. So okay, so to put things in the context of physical cosmology, I'll try to connect things to the current Hubble tensions. Of course, Eleonora will give a talk specifically about the Hubble tensions. I don't know exactly what she will talk about, but anyway, to put the problems forward, I'll try to put things in the context of the standard model and the current tensions. So to go forward, what do we do in precision cosmology? We try to basically understand the dynamics and behavior of the universe first. We can use different methods of reconstruction. And we can use different statistical techniques and of course high quality data. When we know the behavior, the next step is usually phenomenology, that we try to model things in an analytical form to basically to see how to understand the behavior of the whatever phenomena we are studying. And then the last step is theory, means that we try to come with a physical model to explain what we observe. So the standard model is within the bigger context of the current cosmology, which is based on the GR, and it has lots of different pieces. We need to know about the metric of the universe. We have dark matter, we have dark energy, we have curvature, we have initial conditions, and we have lots of astrophysics involved. The standard model is phenomenologically pretty simple in the sense that we can describe it by just 6 parameters, as you all know, because we assume the universe is flat, we assume homogeneity and isotropy of the universe, which we come with the FLRW metric. We have dark matter, which is cold, weakly interacting. Cosmological constant is there as a dark energy, and we just model the whole early universe with the power of form of pre-model spectrum, which suggested by simple single-field inflationary models, and is pretty well established in some sense. So we should realize that the standard model is a combination of assumptions. So it is not a model which has a very deep fundamental background, let's say, from the particle physics. It is a combination of assumptions, but it's a model which is working pretty well. So in 2023, when we look at the type 1a supernova, the residuals, everything looks pretty fine. When we look at the Cosmo microwave background, again, we can go to very high multiples, and then we can see that, the data fits, the model fits the data pretty well in the residual space. 30 years ago, we had nothing. Some of you may remember. When we go to the large-scale structure, let's say baryon acoustic oscillation or redshift distortion, again, the model works pretty well. By model, I mean the standard model plus GR. And, we are trying to have more and more spectroscopy. SDSS 4 basically finished 2 years ago, and now we are basically waiting for the DESI and Euclid. So there is some hidden competition going on between these two surveys. Of course, I'm on the side of DESI, but I know the Europeans are more inside of Euclid. But anyway, both these surveys would be very important to tell us what is really going on in the large-scale structure of the universe. So a standard model is a combination of reasonable assumptions, a combination of assumptions with a combination of reasonable assumptions. And everything looks fine, but, there were some tensions which happen. And that's why I want to put my talk mainly on this context, because this tension happened when Planck 2013 results were announced. And I remember that, fitting the standard model to the CMB data, which, Planck had a much better quality than the WMAP9 at that time, resulted to a Hubble constant of 67, which was substantially lower than 74, considering the tiny error bars which Planck had for the Hubble constant. And things got worse by time when Schu's analysis, had some reanalyzed their combination of Cepheids and supernova. So the problem persists till now. After 10 years, still you have the tensions. And the tensions are not only about the Hubble constant and CMB. We can see that in the BA of the Lyman alpha forest in the large-scale structure. We can see that in the weak lensing slightly. We call it, kind of a S8 tension that, the data fitting the Lambda CDM model fitting the CMB data and fitting the lensing shear results to a slightly different part of the parameter space. So we are dealing with a very complicated situation, which we have multiple suspects. There are different tensions in different parts. We have different kind of data, which can have different systematics and different unknowns in them. And the problem is that, okay, so where should we look for the suspect, and what can be the problem? So here is where, I start the statistics part that, okay, what should we do? How to resolve the tensions, or how to resolve and move forward in this context of the problems which you face in the standard cosmology. So one thing which, up to 10 years ago, many people, considered, including myself, was that, okay, it's statistical fluctuations, it goes up and down. Still, we are dealing with such a huge universe. 67 and 73 is not big deal, they are close to each other. But when we are doing high precision analysis, things become more tricky, in a sense that having like a 4 sigma tension is not something that we can just neglect and said that it is related to the just statistical fluctuations. Systematics can be in one or some of the data. This is something which I will bet on myself personally. I will go more on that later on, that why I bet more on the systematics, even though I work myself on lots of different models and phenomenology and theory. But one thing which is very, I will clarify more later on, is that it's very difficult to resolve the tensions by minimal modification of the current standard model. And that is something that, give a hint that, okay, maybe something is wrong with the data or some of the data, and we should look for that. Another approach, which there have been hundreds of papers, is about extended models or new models, which they try to alleviate the tensions. Majority of these works are not really resolving the tensions. Majority of these works are just having more degrees of freedom, and by having more degrees of freedom, you inflate, you expand your parameter space, your confidence balls. And by inflating your confidence balls, basically you have more overlap between these contours. And then you say, oh, look, it's not 4 sigma, it is 2 sigma. Okay, it is fine to do that, but yeah, I mean, it's a bit of overselling involved in majority of such works. Okay, so what do we do? Now I'm getting more towards the topos, which I'm going to introduce. So there are various reconstruction approaches, parametric and non-parametric, that people try to understand the behavior, let's say expansion history of the universe. And then based on those reconstructions, people try to come up with the phenomenological or theoretical approaches and models. And this is the way which I usually propose to do, when we do reconstruction, then we do phenomenology and then theory. And then we can also continuously look for systematics in various data. So I will visit all these points one by one. And but then the point is that, okay, when we do all these analysis, when we do all these modelings, we have lots of models, and how do we compare the models? Okay, so let's go to the actual old fight between Bayesian and frequentist. So there are two general approaches in statistics that they try to find the consistency of the proposed model with the data. The frequentist approach is basically assuming a model. You try to find the probability of the observed data, and it should not be insignificant. It means that you should basically have a reasonable probability or p-value when you derive this probability of the observed data given the model. This requires lots of careful simulations, and you need to have a good understanding of your error matrix. Many of these things developed a lot in the last 20, 30 years with the power of the computers, because now we can do all these large simulations. The Bayesian approach is very interesting, very popular, particularly in cosmology. It looks like a religion that, it's like everyone is following that blindly. And that's why my talk would be a little provocative in that sense, because, I'm trying to touch some of the caveats of the approach. It is very prior based, and also simplicity of the proposed model matters a lot when we do the model selection, model comparison. And in all these things, the chi-square analysis plays a crucial role in calculation of the likelihood, which is again one of those issues which is accepted not blindly, but is accepted widely by the whole community, and this is basically the only metric which is generally used when we do statistical analysis. So yeah, likelihood, generally we use chi-square. You have the covariance matrix, and then we try to have the model, and you have the data. And one thing which I try to now start with is that the analysis seems very straightforward. We have the data, we have the model, we have a covariance matrix, and so yeah, we can derive the chi-square. We can calculate the probability, the basic goodness of fit, depends on the degrees of freedom which we have, and that should be enough, right? So why should things be complicated when we have a model? Because the data directly can tell us what is the goodness of fit. The problem arises when we don't know the exact error matrix. So when we don't know the exact error matrix in large part of cosmology, people try to work with the diagonal part of the error matrix to make the reduced chi-square around 1. So it means that if you have, for example, 2,000 data points, you need to get a chi-square of around 2,000, so you have a reduced chi-square of around 1. And this is a real issue in almost every pipeline in cosmology. And the problem here is that if you have two models, for example, it's a very old paper, I think it's about a paper about 15 years ago, which was showing that, okay, if you have a kind of a, whatever type 1 is supernova data, and if you don't know this sigma systematics, so if you just increase it slightly, even you can feed the Milne universe reasonably well to the data. So your lambda-CDM is fine, but I can basically feed the empty universe to the data and prove that, okay, we don't exist because the universe is empty, which is interesting, and it's not something old. This is, for example, a very recent paper with Benjamin and Ryan that we just analyzed this Phantom Plus data, which is now in every pipeline, and you can see that when you the chi-square of the best fit lambda-CDM model, when you do a proper frequentist approach, it is really at the lower side. And it basically means that, the covariance matrix of the data is overinflated. And so it needs kind of a treatment. So this is an issue that still persists even currently right now. And this is a data which is in most of the pipelines and people use. So what people do in such cases mainly, then you said, okay, instead of chi-square and goodness of fit, which is very much sensitive to the size and the understanding of the error matrix, let's go with the delta chi-square. So when we go with the delta chi-square, things is better because you find your best fit value, and then when you find the best fit value, depends on how distant you are from this anchor, which is your best fit value, you try to solve the problem. And to do that, we usually use Bayesian analysis. Again, it's a prior based, and the posterior probability is highly proportional to the likelihood and the prior probability, which we all know. So here is a topos 2. So everything is fine, but let's not forget that when we do the Bayesian analysis, most of the time we assume that this normalization is 1, and the prior probability is 1, which means that we assume that we are assuming a true or correct model. So we always, so in practice, what does it mean? It means that, no matter what model you use for whatever data, you always get these beautiful contours because you assume that you are using the correct model. And it's a very important issue because if we don't assume the correct model, the results would not be also correct. And this is something that we should always have in mind when we use a Bayesian approach. And this problem can also propagate when we do the model selection, in the sense that when we have some models and we want to find out which one is better, we usually use Bayesian evidence, which is basic integration over the likelihood and prior over the whole parameter space. Of course, people use some approximation like nested sampling in the parameter space to make things faster. And when we derive this ratio, then basically it says that which model is preferred over the which other model. Generally, people use the Jeffrey scales or this Cost-Rafferty scale, which compare the Bayesian evidence between the models and said, okay, if a model to another model is preferred strongly or very strongly, or they are comparable. This is the topos 3. How reliable are these scales? So the fact is that these scales are not really that much reliable. So these are the works that have been done from many years ago, but to put this in a context, I go back to the Hubble tension and some cosmology analysis, that why these Jeffrey scales or the Cost-Rafferty is not maybe that much reliable when we are comparing models. So going back to the standard model, let's solve Hubble tension with the evolving dark energy. Since I don't want to piss off anyone, I'm going to criticize one of my own models, which we introduced a couple of years ago with Xiaolei Li, which was called PEDE, phenomenologically emergent dark energy. The idea was very provocative, that dark energy doesn't exist in the past and it appears, sometimes earlier, and asymptotically go to the W of -1. And we generalized the model, which we called it the J, the generalized emergent dark energy, which had both lambda and PEDE in it as two special limits. That when the delta is equal to 1, it gives you PEDE, delta equal to 0, it gives you lambda. The equation is very simple. It's actually very simple if you go to the depth of it. So I have this model which, if delta is greater than 0, it basically it supports emergent dark energy. Means that dark energy is an emergent phenomenon. It was not there in the past, and it is appearing at some point with some transition. So the idea was mainly, it's a very old idea I had from many years ago, which was to solve the Cosmological constant problem, because I didn't want to have the fine tuning. I didn't want to have dark energy and appears, but in the concept of Hubble tension, it became pretty interesting. So we did the analysis. This is actually the work with mainly the Eleonora's group, which we did together, and we saw that okay, the JEDA works pretty well. When we deal with the Bayesian evidence approach, we realize that comparable to the lambda CDM model, even though it has 1 more degrees of freedom, the base factor is about 6 and 5. And when we look at the Jeffrey scale, this is basically very strong preference of the JEDA towards the lambda. Okay, cool. So this is the place that many people come and said, okay, it's a great discovery, and I have a model which basically kills, the other model, and that's it. That's what it is. But the problem is that no, we might have a model which might be better than the other model, but it doesn't mean that that model is really properly validated, and it basically can resolve all the problems. So I will come to the context of the validation later. But one reason could be because these scales which we are talking about might not be very well appropriately set to decide that which model is better than which model. So this is a paper which we had with Ryan last year, and we just showed that this distribution which we are talking about is highly sensitive to the distribution of the base factor, is very highly related to the model that we are studying. For example, the data is based on model A, and you're comparing model B with model C. So all these combination matters a lot, that how the distribution of these evidences should be when we do, for example, large number of simulations. And the result is very interesting in the sense that you might have cases, particularly when the quality of the data is not very well, that your wrong model might have a positive evidence of more than 5 or 6 with respect to the true model. And so if we just do this analysis without this background analysis, we would say that, oh, this is strongly preferred to the other model, while in fact it happens with some probability that your wrong model may have the Bayesian the evidence ratio of more than 5 or 6, as we see here. So this is a very interesting paper. I suggest you to read that to understand what is going on. And the subject is pretty, it's not something new. The Glenn Starkman group basically discussed that many years ago. The paper is never published. I think some of the religious people in the community stopped that from publication, but it's on archive. It's a very interesting paper. Then there's a paper by Jenkins and Peacock. Savas and Juan Garcia have a paper on that, which discussed about how priors are important in that, and the Joachim. So this subject is very important, rather than just using these Jeffrey scales and moving forward. Okay. Next tapas is about the validation. So what to do? Now we know that relying on this Bayesian evidence can be tricky. So what can we do? Okay, the problem is also another fold. Another fold of the problem is that sometimes we are dealing with the case that it's not about preferring one model to the other model, or if you are confused preferring the wrong model to the right model. The problem is that what would happen if both models are wrong? So we are dealing with some models, model A, B, C, D, and they're all wrong. None of them are the correct model. Can we use Bayesian evidence to help us in this case? And the problem is that with the current machinery which we have, it's not possible. For example, this is a work which with my students and Ryan and Benjamin, we showed that if you have the data based on, let's say, transitionary dark energy model, and then you compare PD and lambda. Yes, the data is closer to lambda, and then when you do Bayesian evidence analysis, your data always prefer lambda to the PD. And while in reality both are wrong. So what to do here? So the problem is that when the model is unknown, finding a statistical anchor is not very trivial. So we need to know where to find an anchor point to connect things to that, and then find out, okay, if we can validate the models or not. So this comes the concept of the validation, which is extremely important. In fact, before model selection, before model comparison, to validate the models, these models are really valid or not. And so there are approaches one can use. For example, use some reliable non-parametric approach. This is a philosophy which I've been pursuing in the last couple of years. So I'm not going to details of all these things, but basically try to use an iterative smoothing approach to go beyond the best fit model, to see that how we can overfit the data. Basically, let's not forget, your best fit model always have a better likelihood than your true model. So even when you do the parametric approach, you have whatever data you have. Even if you assume a correct model, your best fit model, the best fit parameter in your model, has a likelihood better than your true model. So it is something that basically is anchoring which you have. And the distribution of this is the fact that help us to basically do the parameter estimation. So we use the same philosophy in a non-parametric way to anchor with the iterative smoothing. So we derive this delta chi-square between the best smoothing, which is much better than the best fit parametric form, and use this distribution to do the validation. So I'm not going too much into the details of that, but it's a very frequentist approach, but it can allow you to validate a model based on a given covariance matrix, and then say, okay, it is valid model or it's not valid model. So results we show here, for example, with the same case that we're using the conventional Bayesian approach, just data could prefer one to the other one. We could see that, okay, our approach could, in 916 cases, in 95% confidence limit, rule out both models, which was very great. Because you could say that, okay, and out of 1,000 simulations, in some cases, some are preferred, some are not preferred, but there were 916 cases we could rule out both models. We cannot say what is the right model, right? Here we cannot say that what's the right model, that data is derived from, but we can say that whatever is proposed are wrong. Okay, so it's an interesting paper which I suggest you to read about model validation. So some application of model validation. So okay, now we know that this is important. We can have models better than some other models, but what if that they are all wrong? So this is a work which we did with Ryan, and we said, okay, let's have a very extensive physical space using the crossing functions. Is a paper I produced many years ago, and said, okay, let's model everything, from the dark energy, dark matter interacting models, evolving dark energy models, modified gravity models, curvature, everything, by introducing a large parameter space, and see if we can still. So of course these models would fit the data much better than the lambda, but is it really validated? And this was what we found, that even give it such a huge parameter space, extension to the parameter space, as in the posteriors which we have for the Hubble parameter was not matched with the Schu's results. So it basically says that, look, you do fit better, but still you cannot really resolve the tension. So this was what we called as ruling out the new physics, recently accepted in PRL. And so it was a very interesting point that, this concept of validation can basically says that, look, there are many solutions, but they may be all wrong altogether. And which something, again, very important coming to the picture, that, okay, now things are suspicious. Okay, so it's suspicious in the sense that, it's that if nothing works, maybe some data has a problem. So this is what I personally try to conclude in such cases, rather than pushing some interesting theoretical model. We usually get attached to the models that we work on. As you work on a model, you introduce it, it has a mathematical beauty, but in generally, we should not be very much attached to the theory. We cannot decide for the universe how to behave. We better see how universe behave and be humble towards that. Okay, so I finished 4 topos. Let's go topos 5. Topos 5 is about okay, when we don't know what to look for. Okay, so the point is that, okay, now we rule out lots of stuff. We ruled out, okay, these models are all wrong, or we know that how to deal with the data, but okay, what to do, how to move forward. So this topos is about importance of non-parametric reconstructions, which can be kind of a guidance for us, that when we are stuck, we have models that are all not good. What can we do? Can we go just get help from the data directly and say, okay, you suggest us what to do and how to move forward. So I go again in the context of the standard model and the Hubble tension. Again, I want to put it there. So okay, why reconstruction can leads the way. So let's go to the early universe and says that, okay, now I want to use the early universe and reconstruction to attack the Hubble tension. So the concept of reconstruction has been there for many years. Sar Breidel's paper, David Spergel group. We were working on this. My first actually ever paper in cosmology, and Subir Sarkar's group. So people have been Planck team. They've been extensively working on direct reconstruction of the cumulative spectrum, because God didn't write in any holy book that it should be a power law, right? So we can have all different models, and the point is that you can have other inflationary models or other form of premodal spectrum that can satisfy the data very well. For example, it's a group of series of paper with Alexis Starobinsky and George Smoot, which we introduced weekly Wipped inflation and Wipped inflation with Diraj Hazra. And so they are not power law, but they fit the data pretty well. They are comparable. And they have a very important characteristic. They fit the data, but in a different point in the background parameter. So what do I mean? Means that when you go beyond this ASNS of the power law from premodal spectrum, when you fit the same data, you may end up in the different parts of the background parameter space. And that's a very important fact, because then we can say, okay, let's use reconstruction. Let me put H0 not 67, I put it 73, and I will put omega matter 0.26 to satisfy the cleansing people, and then let's see what would happen. So that's what we did. And with Diraj and Tarun Suradip, and also in the next paper with Ryan, we said that, okay, let's fix the parameters, omega matter of 0.26 and a Hubble parameter of 73, and then see what I get. And that's what we get. You get a very ugly form of the premodal spectrum, but if you use that form of premodal spectrum rather than the power law, you end up in this part of the parameter space. Okay. So this is a reconstruction which give us a hint. Of course, I would like to emphasize about the beauty of the modified Richardson-Lucy deconvolution algorithm. I think Wuyan will give a talk about that today afternoon. So if you are interested in this deconvolution approach, attend his talk. So having that reconstruction, that idea that ugly form works, I go to the phenomenology. So okay, now I try to model it, help the reconstruction to model the form. So we find this form, which basically was very interesting to resolve many anomalies. And mainly A-lens and curvature anomalies. So in a sense that when we have the lambda CDM model, we have these things that in the A-lens, which is not a real parameter, is barely consistent with 1, and it prefer larger value. And or if you allow the curvature, it likes the curvature not that much consistent with the flatness. So we realize that having this form not only resolve, you see that this blue PDFs consistent with the flatness and a lens of 1. Also, it can shift the Hubble parameter slightly to the right direction. So, again, the two-dimensional thing. So it's very interesting that again reconstruction can lead us to come with a reasonable phenomenological solutions, and phenomenology can lead us to the theory. So it was another PRL we had this year with Fabio Finelli and Achille Antoni, which was basically fruiting our approach from the reconstruction and phenomenology. So okay, now I know what should I look for. I know that I need such a form of premodular spectrum. Now let's, I leave my inflaton and play with the potential in a way that to give me this form of the premodular spectrum. Basically cooking an inflationary model potential, which results to the form which I know that it will work. Then I would say that, okay, I found the early universe solution to the problem. Okay, cool, I'm on time. So current status, it's an open problem. Many tensions and hints for systematics. Again, since the problems are so multidimensional, I would be highly suspicious that there is a systematics in some of the data. There are many models proposed, including my own group, but none of them are really convincingly works. Some of them are statistically better than the lambda, but it's not like that they all pass all the validation tests. And again, importance of the validation tests. And then since we cannot really come up with a solution which solve everything, that helped the lambda CDM to still remain there, and survive. So TOPAZ 6 is that, okay, when we deal with such cases, it's important to do model-independent consistency test between different data. So it means that now we don't know what is going on. Let's compare the data together, which again, very important context, because we don't want to just fit models to different data. But it's okay if data internally are consistent or towards each other. So there are approaches. One of them is Gaussian processes for falsification, which again, I suggest to people. There are 3 papers, 2 of them are very classical papers by Eric Linder and Alex Gimby wrote many years ago, more than 10 years ago. And there's a recent paper by Benjamin's student and some of us, which is basically how to use Gaussian process in a proper way, not to make it biased towards the mean function and the hyperparameter space. And it can be used to test the consistency of different models. So if someone is interested in Gaussian process, I suggest these papers. And it can be used to test that if 2 different data of very different nature are consistent with each other or not. So future perspectives. So things are good. The key point here is that the data is getting much, much stronger. So I go very quickly here. We would have TRGBs, the James Webb, we would have lots of more interesting results from the TRGBs. We have a strong lens systems, already competitive. Now we can have about 2.5% precision on the Hubble constant from the strong lens systems. We have tens of supernova coming. At the moment we have 1,500, but we would have hundreds of thousands of them at the time of LSST, Rubin and Roman. BAO, RST, both DESI already observed more galaxies than all spectroscopic surveys combined so far in 1 year. So with 5,000 fiber, DESI is gonna basically, kill it. Hopefully faster than Euclid. But so, and there are already little advertisements that, survey validation and the early data release is there already in archive. We are analyzing the first year data. So things become substantially better. We have gravitational waves again, by having, there were talks about that, by having the bright sirens and dark sirens, we are basically pinpointing lots of interesting facts about the universe because it gives us a very new kind of a data with different systematics. So things are getting great in the primordial sense with the CMBS4, things become again great, with the we would basically can distinguish many early universe models from each other. Then we can go from the 2D of the CMB to 3D of large scale structure. Lots of works going on to use large scale structure data to test the early universe models. So everything looks great. And the data would be substantially better than anything else. But this is again related to the TOPAZ 6, is that with the higher quality of the data, the role of systematics will become more and more prominent. What do I mean? Means that, when you have low accuracy, If you have some inaccuracy, that's some bias, but if you have a large uncertainties, it's okay. If it is 25 plus minus 5, if your 25 is biased towards higher values a little bit, 26 is fine. But if it is 25 plus minus 0.3 and you have about 1 value of the bias towards a larger value, then you will come up with the fake discovery. And now with the power of the data, more data, we know that in a very back of envelope calculation, you would have much better precision. The role of those systematics would be very important, and these systematics can come also from model assumptions. Is that when you assume a wrong model in your pipeline from the A to Z, for example, we use GR and lambda CDM, and then we want to do RST, and then we use the F sigma 8 data to test some modified gravity models. These are all introducing biases in our analysis. And it can go to the BAO, it can be in the supernova, the way we are anchoring them, as well as the cosmological background. So any data we use. So these assumptions and systematics which you don't know, they can all something that we should be worried about. So my conclusion, there are many statistical tools are not used appropriately in cosmology and astrophysics. So I didn't talk at all about the machine learning things, right? So these are the tools that everyone is using most of the times in the wrong context. So I think there would be talks about that. So I left it all without talking about that. But there are many tools which are used in an inappropriate way. So we should be careful what we are doing. The Hubble tension is interesting. It's at least it add juice and flavor, spices to the cosmology in the last 10 years. Otherwise, you could get really dead bored. So we know that some problem is there. So there is alternative for for models to explore, but we should be careful not to oversell them. It's good to propose models as an alternative models, but let's not to say, oh, we are going to kill everything. The fact that tensions are not resolved with the minimal extensions is something that, to me, is a very important hint towards systematics. So it's very important to look for all different systematics from the model assumptions in the pipelines to not properly understanding what is going on with the data or physics of the data, or it can be a combination of both. Maybe it could be systematics and some new physics. So anyway, we should be very open-minded towards all possible solutions. And again, the last point, which I think is extremely important, with the high quality of the data, the role of this bias and inaccuracy is extremely important. So we should be much more careful and stressed to solve the problems in a proper way. Yeah. Okay, thank you.
Thank you very much, Harman, for a great talk and for finishing in time. That was great. There were a lot of interesting, important points in Harman's talk, so we have plenty of time for questions. We'll start with.
Thank you, Arman, for the wonderful talk. So I have a quick question. So you talked a lot about the systematics in the data, but do you think we could resolve the tensions by also working on the theoretical systematics, on the systematics of the theory? Do you think this would help to resolve the tension specifically? I
mean, it's very intuitive. I think there's some problems with some of the data. I would not be surprised.
Problems in the theory, like, for example, the nonlinear prescriptions that we are using.
So. Yeah, it could be. Or for example, type 1a supernova. I mean, we don't know the physics of type 1a supernova. Lots of error budgets put by hand, right? I mean, there are people who push a lot for evolution of the but okay, for example, there is no dark energy. Well, I'm not going that far. But even you have a little bit of evolution, or a little bit of not understanding, that can basically plays a lot with the error matrix. Right?
Thank you.
Or the way we anchor them with the sets.
Yeah, thanks for the talk. I have a comment and a question. My comment is that I very much agree with doing the two kinds of analysis, one based on a given model and you test a model or alternative models, and on the other one, in a way of validating model to do something more non-parametric, right? Of course, there is pros and cons, because if you do something non-parametric, you have less precision in getting the errors of the parameter of the other parameters, let's say, or because you have more degrees of freedom. And in relation to systematics, I think the best way to go is to understand your instrument, right? So
Understand what? Sorry, if you keep the microphone closer to your mouth.
Sorry. Yes. No. That the best way to understand the systematic, to deal with systematics, is to understand very well your instrument.
Exactly.
And then that's the reason that it's very important to do end-to-end simulations, all kind of tests with your instrument. Just looking at what is the impact of each of the non-idealities that you have in your instrument. Oh, okay. This is the comment. About the question, I'm not sure I understand. When you show this plot shifting this H0 value from Planck to match the supernova value, you talk about something non-parametric there, and but I didn't see any widening of the contours of H0. If you do something non-parametric, in principle, you enlarge your error bars or your contours.
I mean, which slide you are talking about? Because I think I didn't show any non-parametric things.
Yeah, in one in which you seem to solve the tension.
You mean this one?
No, before. That one. Yeah.
This one. Okay.
Yes, so
yeah.
You shift it.
So this one, this form is fixed.
No, sorry, it was not that one. Another one in which it seems that you assume a non-parametric form for the primordial power spectrum.
So you mean this one?
There was another. Okay, maybe we can.
Or this one?
No, you have many.
Yeah. Okay. So here, first of all, this is parametric. This one is parametric. It's just we are adding a hyperfunction along with the curvature, along with the parameters of.
That was not the plot I was talking about. Sorry.
Okay. So if you could find, you can let me know later. But yeah.
Okay.
Yeah, but okay. About your first comment, I absolutely agree that the understanding the instrument is extremely important. And one problem is that in some of the compilation, let's say again type 1a supernova, these data coming from the combination of data from various instruments, different telescopes, right? They have their own selection effect, they have their own probably instrumentation or systematic. So I agree that understanding the instrument is extremely important along with the other things. Yeah.
More questions?
Yeah, actually related to that point, I had a question about the systematics in the measurements. So, as you said, data from supernova, for example, come from different instruments, but they can also come from different, like, constraints on H0 can come from different probes completely, like strong lensing. And the same for DSA, you can have constraints from weak lensing, from galaxy clustering, from galaxy clusters. So it seems to me that having systematic explain these tensions when you have so many different observables and instruments is unlikely. What is your comment on this?
So you mean that since these constraints are coming from different data, kind of a data, so they cannot be systematics?
Well, not that they cannot be, but it just seems more unlikely. Like, if you measure H0 supernova
okay.
and strong lensing.
Okay, let's go here. Okay, I'm not going to the nature of the data. All right. Let's go to here. We have a standard model fitting the Planck data for the sigma 8 or S8 and omega matter, and we have a weak lensing shear from two different instruments combined. So they are not matched with each other. I think we can interpret it or give possibility of everything. First, the model has a problem. Two, maybe our understanding of weak lensing shear, of course, people of weak lensing here would not be happy about that to hear that has a problem. Or some understanding of the CMB has a problem. So I think all is possible. That is my point. So we should just, usually we get so angry, they say, oh, CMB is so clean, everything is perfect, right? I mean, the A-lens issue, that A-lens is not equal, is barely consistent with one. A-lens is not a parameter, right? Of course, people would be upset if you said that, okay, yeah, we may not know the answer, but I think we should be open-minded to be able to interpret it in different ways.
We still have time for more questions.
Thank you for the very nice talk. Concerning the third point of your conclusion, I didn't understand the relation between saying that if simple extension from the CDM does not solve the tension, it means it has to do with some systematics. Maybe another phenomenological model is also another phenomenological model, so it should not be solving any tension.
Actually, you're right. You're right. I mean, if we can find a fundamentally different solution, that's yes, that helps. In fact, it is true that a huge breakthroughs in astronomy has been related to the cases that we could not really solve some anomalies. Let's say, the heliocentric and epicycle models, right? The people add more cycles and cycles and cycles could not explain the data, right? And heliocentric was not working. It was there because it was, circle. It was not ellipse, right? So it could be the case. It could be the case, but I would say again that we should be really open-minded to look for everything. I mean, and that's why we work on the theory models, right? I mean, this one spectrum, we are really pushing that. We are thinking that this could be the answer. But I'm saying that at the same time, we should also look for the systematic. We should just have open eyes on everything.
You have time for one last question.
In this new model that were the power spectrum, where would it show up other than in the tension? So in H0, would you also see it in cross correlations, or like what are other probes to check these new?
You mean pre-model spectrum one?
Yeah, the one you were pushing.
So I mean, we didn't cross correlate the data. We just fit the model to different data, right? And so yeah. As I said, I think it was related to the point that mentioned or colleague that when you have a non-parametric approach, you have many degrees of freedom. The contours become large, and that's why I go to phenomenology, because then I can mimic that behavior with few degrees of freedom, right? So then, reducing degrees of freedom, I can have a smaller contours. But yeah, I mean, fitting this form basically to different data, we could see, for example, have a better overlap with the big lensing data. This is from the kids. We have a better overlap with the H0, S8, and here with A lens and curvature, we were consistent with the zero curvature. So the whole point is that this model can satisfy observations better, or being intentional. A cross correlation usually is done when we want to, looking for a phenomena by in both data when the significance is very low. So here is just the proposed model which can fit the data better.
Okay, thank you very much. Let's thank Armin again.
Thank you.
Ya, Zoom. Sì. Fa una pellicola se no.
Metti Zoom.
Yes. So shall I share my screen? Yes.
Change the discipline. You have to mirror the display in the settings. Settings. Now, settings. No? What is the settings? Second settings. Settings. Display, right? In the display. Display. And then mirror. Yeah, in display. No, it's. But no, don't see here. No, just yeah, mirror. We have to go again. The same. I think you should look at it.
Okay, so which one?
The mirror, the next one.
Okay, yeah, sorry about that.
You're showing yeah.
So
now we'll come here. All these.
That should be fine.
And network symbol way using that way. Maybe just be the inclusive. Just go.
Yes.
So good from that. Just undo this. There is some.
Is connected? Yes.
Yes, it's connected. Can you click on the next slide manually? Yes. No, this okay. This doesn't work. It's okay. It's ready, but it's less.
Okay,
Thank you.
Okay, sorry for the delay. So we continue with the second talk. So Paco is going to talk about cosmology in the machine learning era.
So thank you very much. Apologies for the delay. I have some movies, so that's why. So yeah, thank you very much to organizer for putting together this amazing conference, and thank you for inviting me coming back. And I'm going to talk about machine learning. So, I believe all of you know about ChatGPT, you know DALL-E and all these things. This is really, I believe, a revolution what we are doing these days. And this thing is also impacting like cosmology and astrophysics. And this is a little bit what I would like to talk to you today. So this is the outline of my talk. Let's see if I can change. So the talk is basically focused about doing parameter inference. So I'm going to start very briefly, about what is kind of the traditional way of doing parameter inference, in particular using sampling statistics. And then I'm going to move into something, like how can we really use machine learning to go well beyond, I think, what we have been able to do. And in my opinion, even something that I think maybe some of us will think that it will be possible to do, like maybe 5 years ago. Then I'm going to go to something much more, let's say, exotic or maybe controversial. That is this whole idea of, can we really do cosmology with one single galaxy? I'm going to tell you what we have done and what we are doing. And basically just to show, if the power that machine learning can have to identify real physics or maybe some numerical things. All right, so the large matter model. So as some of you know very well, this is very well established model, right now the best model that we have. And this model has some parameters. And one of the main goals of cosmology is to constrain the value of these parameters with the highest accuracy, right? Because we want to learn about fundamental physics. So the smallest, the error bar that we can put in these parameters, the highest, the confidence that we can say, about fundamental physics. What is the nature of dark energy, the sign of the electron masses, and all these kind of things. So how we do this in practice? So what we do is to carry out observations. So for instance, imagine that you measure the position of galaxies on the sky, and the thing is that we don't really know how to work with that data. If someone gives you just the position of galaxies, we don't know how to work with that. So what we usually do in cosmology is to compress the data into a low-dimensional vector, like for instance the power spectrum. And from the theory side, what we do is that we have some cosmological parameters, and we make theoretical prediction of how this observable will look like given some cosmological parameters. And then basically we compare what we measure with our theory, and this is the way that we do parameter inference. So I think the important question here is like, what is the optimal way to compress the data? What is really the best way to compress the data here in order to maximize to minimize your constraints? So, as all of you know, this is something that it has an answer for a very particular cases. So if you have a Gaussian density field, we know that the power spectrum completely characterizes the statistical properties of these fields. And we use the power spectrum, we are guaranteed that we will be able to constrain the parameters as good as possible. For generic non-Gaussian sample statistics, this is an open question. As far as I know, this is mathematically intractable. We don't really know how to do this. So let me summarize this part. The lambda matter model, we really want to constrain the value of cosmological parameters. It's one of the most important questions, I believe, in cosmology. And we don't know how to really do this for, let's say, generic Gaussian density field, let's say for galaxy cluster. So in this case, what it has been done traditionally for the last years has been basically to compare different summary statistics. Let me use the power spectrum, let me consider the bispectrum, the trispectrum, let me use a Helmholtz function, Boyce function, all kind of things. And in many disciplines in physics, we use the Fisher matrix formulas that will allow you to, without doing the experiment, will allow you to compute, how well can you constrain some parameters given some observables. So imagine that you have some parameters like this, and you have some summary statistics. If you are able to compute this quantity, this is the Fisher matrix, then there is this mathematical theorem, the Kramer-Rao bound, that tells you that the variance of an optimal unbiased estimator will be larger than this. And this is basically a way to get an idea of how well you will be able to constrain parameters. So we use this in cosmology all the time, but in general, we tend to use this in the linear regime or maybe the perturbative regime, basically because computing these kind of things in the fully nonlinear regime for generic summary statistics is not something simple, and it's not a trivial thing. So basically, in order to provide some kind of data where you can do this calculation in a systematic way, we have run this very large set of simulations that we call the Quixote simulation, this very Spanish name. This is a set of, is way more than this. I got so many complaints from the system administrator, but we have more than these simulations. We have, like standard lambda Kodal matter parameters, but we also have neutrinos, like W, simulation where you vary the DC mode, with primordial non-causalities like local, orthogonal, equilateral. We recently have simulation with parity validation, and we also have now with modified gravity. Anyways, the important thing here is that these simulations were designed basically to be able to make this kind of Fisher matrix calculation for any generic summary statistics. If now someone can and give you the Minkowski functionals, you can use the simulation and basically you will be able to use the Fisher matrix and you will be able to compute how well you can compute constrain the value of the parameters. I'm going to mention this later, but in case I don't have time, all the data is publicly available. You can download the petabyte of data. You have a petabyte handy. You can just connect to our cluster in New York, and you can just use all the data there. So yeah, I think very nice. But I don't want to spend a lot of time here. I just want to mention that many people have used this simulation. Yesterday we had a lot of talks also with other simulations. People have looked at, for instance, the Boyce size function, the Mark power spectrum, bispectrum. I think maybe I will talk about the PDF. There is a very generic conclusion here. And the conclusion is that, as long as you go to the non-linear regime, and as long as you use things beyond the power spectrum, there is a huge amount of information that is there. And it's maybe not surprising because the power spectrum in the non-linear regime we know is suboptimal. So this is really a motivation to go beyond the power spectrum and also to go to smaller and smaller scales. So the problem about this is that, in the nonlinear regime, probably we will need numerical simulation, that expensive. But probably the main thing I would say is that we will need to deal with varying effects. This is a regime where things like AM feedback will not only change the properties of the galaxy where it resides, but it will also affect the distribution of matter and gas on much larger scales. And the problem is that we don't really know much about these astrophysical effects. There is a very large uncertainty about this. So ideally, we would like to marginalize over this, just to be conservative, until we really understand all these processes much better. Let me summarize. So, the lambda Kodal matter model, we want to do parameter inference. We don't know what is the optimal way to do this. Until basically, very recently, people have been just using summary statistics and basically compare them. And the problem of this is that either you have 1 million graduate students and you give to each of them a different summary statistics. This is not really practical, right? There is an infinite number of summary statistics. We cannot really go to each of them. So now let me talk about how to do a very different way, how to tackle this problem in a very different way, which is using machine learning and doing all this field-level likelihood free inference. For this, let me talk about the Cosmos project very recently. So Cosmos was designed as a project to create bridges between cosmology and galaxy formation. Marita mentioned in her talk on Monday that usually, these are kind of two communities that we don't talk too much, and this is completely true. And at the end of the day, we both are using galaxies. So we will benefit a lot to talk to each other. So basically, the way to create these bridges between these two things, in our case, is using state-of-the-art hydrodynamical simulations, and very importantly for us, like machine learning. This is really like the key for us. So this was basically the idea of why we created this CAMOS project, which stands for Cosmology and Astrophysics with Machine Learning Simulation. It's a very large set of more than 10,000 simulations. And now I have some videos, so this is why I created all this mess, because I wanted to show you this. So this is, for instance, one hydrodynamical simulation of the 5,000 of them that we have. The other 5,000 are just traditional bodies. This particular simulation has been run with the RANSYS code, and what you can see in blue is the density of the gas, and in red you can see the temperature of the gas. And you can see clearly why we need to run this hydrodynamical simulation, right? This is a mess, I would say. You have galaxies that are forming in the gravitational potential well of dark matter halos. Galaxies are accreting gas, maybe from the filaments. Galaxies are forming stars, the star is exploding. Some of them will form black holes. The black holes will emit, there will be agent feedback. And galaxies are also colliding and merging. It's a fucking mess. And this kind of simulation gives you like a very detailed predictions, not only about the properties and the distribution of dark matter, but also about the gas property. Things like the temperature, the density, gas, phase space, and everything. So you have like 5,000 of this one. Another thing that is very important for us is that we should not rely on a single code. So right now, cosmological hydrodynamical simulations, we don't really have enough resolution to resolve astrophysical processes like the formation of stars or the formation of black holes, or how a supernova will hit the surrounding gas. So for all these things, what we have are basically phenomenological models that we call subgrid models that are physically motivated, but at the end of the day, these are kind of approximations. You should think in all these kind of simulations as approximations to reality. So if you really want to use machine learning and you want to go into the nonlinear regime and marginalize organic effects, I think it's very important that you don't rely on a single code. Whatever model that you develop, it should work at the very least on all possible kind of hydrodynamical simulations, run with different codes. So let me show you here a movie where we have 4 different simulations, same initial conditions, same cosmology, let's say fiducial astrophysics, just run with different codes that employ different subgrid physics. So in blue, again, is the gas density. In red is the gas temperature. And you can clearly see, for instance, this one, Simba, how it's hitting the AGN like way more than all the other simulations. And let me emphasize that all the simulations were more or less calibrated to reproduce things like stellar mass function or redshift 0. So to some extent, all these simulations will give you the same answer, a redshift 0 for the summer statistics that we typically use. But when you look at them in detail, this is for instance the electron number density, there are like very big differences. And there is no one better than the other. I mean, if you talk to some people, they will tell you that the model is better, but there is really not. All of these are approximations. So we need to really build our models to be, that it doesn't really depend on which particular simulation we are using. So this is the metallicity. And you can see that in some cases, maybe two simulations are more similar to each other. And let me finish with the gas pressure. So in CAMOS, what we have is basically we have run simulations with 7 different codes that I think represent really most of the codes that are out there. If someone else has any more codes, please let us know. It will be nice. It will be great to include it. But yeah, so we have really 5,000 simulations run with 7 different codes. And finally, is that when we run the simulations, ideally, if you want to do cosmology, what you want to do is to maybe change your cosmology because you want to train machine learning models and you want to give them like different cosmologies. But it's also very important to change the astrophysics. So what you can see in these movies, this is again gas density and gas temperature. These are just different simulations from CAMOS. Each simulation has a different cosmology. Each simulation has a different astrophysics. And you can see that things change dramatically from one case to another. And the whole idea here is that we don't really know what is the correct way of astrophysics, how really this thing operates. So we will give basically the same weight to all possible cases. We will treat all the possible astrophysics in the same way, or in other words, we are going to marginalize our baryonic effects. We are going to treat all of them in the same way. So typically, either we will vary for astrophysical parameters, or we recently basically we go all the way to vary all the astrophysical parameters that there are in some of these codes. Okay, let's come back to parameter inference. And let me talk about galaxy cluster and how we can use machine learning, and in this particular case, like deep learning, to really tackle the problem in a very, very completely different way. So imagine that each star here represents a galaxy. This is a survey, and you have a set of galaxies that you have measured. You basically have the position of the galaxies. So I will argue that probably one of the best representations to really model this data is as a graph. Usually in cosmology, we tend to use grids. You can ask me later, but I think these are really something very inefficient. I think the best way to really represent the data is a mathematical graph. And in a mathematical graph, you can completely describe the graph by three things. You have the nodes, which in this case represent the galaxies. And the nodes can have some features. So this is typically like a vector. You can think of these like the composition, the velocities, maybe a stellar mass. There is also a set of edges. So, two galaxies might be connected by some edge. And these edges can also have some features associated to them. For instance, can be the distance, or can be the angles between these things. You can put whatever you want. And then there might be some global properties, like the total number of galaxies, or the tidal tensor in this entire region, whatever you want. So, in machine learning, deep learning, there are models that can work directly with graphs, which is very nice because galaxy clustering, the problem is the data is sparse and is irregular. So, graphs are really, really the best way to represent the data. And there are models that can directly work with the graphs. So let me explain a little bit how these things work. So the thing is that you will have this graph, and you will put the graph into one of these graph neural networks. And what this graph neural network is doing is basically to update the properties. So, you initially start, let's say, with position and velocity. And what you're doing is basically updating these kind of numbers. And these numbers will, of course, become something abstract that we don't really know. But the idea is the following, is that imagine that you start with this edge. And what you do is, you take all the features from this edge, and you take the features from the nodes connecting to this edge. You put everything together, and you pass this through a non-linear function. And this is, as you can imagine, parameterized typically with a fully connected layer. You can do the same thing with the nodes. So in the nodes, imagine you have this node. So you take the features of the node, and now what you do is to consider the connections to this node, like this, in this case, these three cases, and you do this super weird thing. The first time I saw this, is like, oh my God. But this just means that this is a permutational invariant operation. So things like the mean, or the sum, or the minimum, these kind of things. And you put everything together. And then you pass this through another non-linear function. That again is probably a fully connected layer. And then, in this way, you are basically updating the properties of this graph. And you can do this several times. You put it one time, you will update all these features. You can put another time, you will update the features. And you can do this as deep as you want. You will end up with a graph with these updated properties. And then, you can do something like this, where now you take the nodes with all the updated properties, you do this permutational invariant operation. If you have some global features, you can put everything together, and you pass this to a non-linear function. And after all this mess, what you end up is basically with a vector or a number. And this is the way to go from a mathematical graph where the data is irregular, is sparse, to this will be the value of your cosmological parameters. And if you put everything together, you can see that there is a lot of non-linear functions. And this is a way to go from the graph directly to, maybe in this case, to the value of the cosmological parameters. And you can do things like likelihood free inference, and you can work at the level of the graph. And one, in my opinion, really beautiful thing here is that we are not really putting any cut on scale. In cosmology, we typically cut on scale. Here, there is no such thing. If you have two galaxies that are as close as possible, the graph will basically be built, and you can extract information from there. So we have applied these kind of ideas to the data from CAMOS. So what we have done is that we have taken 1,000 simulations, in this case run with the Astrid model. For every simulation, we have like a galaxy catalog, typically will be like 1,000 galaxies. And this is the way that our graphs look like. You see, not all the points need to be connected. And these are also from very, very small regions, only 25 megaparsec. And every graph is characterized by a different omega matter, as it might, and every simulation has also different astrophysics. And the only thing that we're considering here is the position of the galaxies and the C component of the velocity. And let me emphasize that, at least for CAMOS, the minimum distance between two galaxies is around 5 kiloparsec. So, if you do like 2 pi or r, this is a very naive thing, but you can say that here, we, in principle, should be able to go to K of 100, something like that. And what we do is, we have all this graph, we try this graph neural networks, and we do likelihood simulation-based inference, and basically we try to infer the cosmological parameters directly from here. Does this work? So let me show you. So this is what we obtain. So let me explain. So for instance, take a look at this point here. This point here is a graph that is coming from the galaxies from a simulation where the true value is like 0.32. You put this into this graph neural network. The graph neural network is going to tell you the posterior mean and the standard deviation of the posterior. And this is basically like the prediction. And the closer that you are to this line, it means that you are really able to retrieve the correct value. And you can see that this works. The only thing here is that these graphs were created with the same code that I used to basically create, to train my model. And I can tell you that this thing will always work. I have done this many times. The real problem here is that what happens when now you put this into a different, let's say, a galaxy catalog created with a completely different code. So, this is for UAM-CSIC, it works. This is for Simba, it works. This is for Magneticum, it works. All these things are basically different codes. This is UAM-CSIC, but this is now varying 28 parameters. Some of these parameters were never seen in the training set. It works. This is for Eagle, it works. This is for Ramsey, it works. There is here at one point that doesn't work. Supernova theta was so efficient here that there is only 2 galaxies in that simulation, so I mean, it's probably expected. And this even works with semi-analytic, which is a completely different way of modeling galaxies. This is for Gaia, and this is for L galaxies. So, in my opinion, it's really remarkable that, in 2023, we are now taking galaxy catalogs and working at the level of the catalog itself. We are going to K of 100. We are doing likelihood-free inference, and we have a model that not only marginalizes over baryonic effects, but it basically works for all these different subgrid models. So, this gives me a lot of confidence that if I apply this to real data, it might work. Doesn't mean that it might work, that it will work. But this is not a trivial test by any means. It's a really So, it would be nice to also understand what is going on. So, this is a work done by this amazing undergraduate student from Princeton who has like papers, and she's still an undergraduate, where basically she combined, symbolic regression with graph neural networks, basically in order to understand what this model was doing. And she was able to derive this formula. And believe me that if you take this formula and you just take the position and the velocity of the galaxies, this will give you the value of omega matter. So I still don't understand what this formula means. I don't really, some people say that, but still I don't really know what is going on. But my feeling is that, this is probably something maybe related to the continuity equation. in the quantitative equation, you have a relation between densities and velocities, and this is really, is really a very tight constraint on phase space. And this needs to be satisfied. And probably this is maybe related to this. In our case, including the peculiar velocities was really the key thing. If you do this kind of analysis only using the positions, it doesn't work. So this might be really like some kind of fundamental relation at the level of phase space that let's say that machine learning has driven these kind of things, because I don't think in traditional cosmology we have never gone to K of 100. All right. So now let me talk about something more provocative, maybe more polemic. And I'm sure maybe some of you have heard about this completely crazy idea about whether we can do cosmology with one single galaxy. So let me emphasize, I'm not claiming this is a super interesting result that we are getting from the simulation. Many people have reproduced the result. This doesn't mean that it's real. It might be real, or might be something, another thing that machine learning has led us to, or it could be some kind of weird thing in the simulations that we don't fully understand. So what do we do? So what we do is that, we have like 1,000 simulations, maybe from the illustrious TNG model. And what we do is to first split the simulation into training, validation, and testing. And let's consider the training part. So, here you have some simulations. You take one, and in this simulation, there will be galaxies, of course. You take a single galaxy, and this galaxy can be characterized by different properties, like, for instance, the stellar mass, the metallicity, I don't know, the maximum circular velocity, all these kind of things. And for this galaxy, you also know what is, for instance, the value of omega mater and sigma A, because you know the simulation, where it comes from. And you can do a very simple exercise. You can just train like a neural network to see if there is any relation between galaxy properties and the value of the cosmological parameters. So you train this, and once this is trained, you go to your testing set. So simulations with different cosmologies, different astrophysics that your network has never seen. You take a single galaxy, you take the properties of this galaxy, you put into a neural network, and the neural network is supposed to give you the cosmology. Does this work? So this is the plot. So let me explain. Take, for instance, this point. This point represents a single galaxy. And this galaxy is coming from a simulation where the value of omega mater is like at 0.28. You put this galaxy into a neural network, and the neural network is going to tell you the posterior mean and the standard deviation of the posterior. This is without making any assumption about the posterior, so this is likelihood-free inference. And the same as before, the closer that you are to this line, the better. So you can see this is very surprising, but this works. You are able to constrain omega mater with one single galaxy with a 10% accuracy, more or less. And this is already marginalizing over baryonic effects, right? Because you have seen all these different cases, at least the way that we model this. It doesn't work for other things. You take a look at these AGN parameters, and it doesn't really work. And, this is one thing that doing this calculation really takes like half an hour. It doesn't really take more. But are you going to write a paper saying that you have trained for half an hour a network, and now you are claiming that you can do cosmology and you don't understand anything? So we really spend a lot of time really trying to understand what is going on. And I'm not sure that this is the correct interpretation. But basically, our explanation so far has been that as you change the value of omega mater, there will be more dark matter in the universe, and there will be more dark matter in galaxies. And if you have more dark matter in galaxies, maybe the gravitational potential well will be deeper, and this will affect all the galaxy properties. This will change your star formation rate, it will change your stellar mass, your metallicities, but that change is really coming from having a deeper gravitational potential well. And this is something very, very different to the effects that, for instance, a feedback can produce. When you have supernova feedback, it's an explosion. This is, physically, is a very different thing than injecting more dark matter. So we believe that this might be the explanation. Recently, from a student from Colombia, the country, not the university, the US, they always get confused. We also took a look at, a completely new set of simulation, Astrid. And, what we also realized is that, if you train your model on, let's say, illustrious TNG, and you apply to other simulations, this thing still works. It doesn't work always, and this is still a problem to make the model robust. But in most of the cases, it actually works. So if you are able to somehow identify the range of validity of your model, these kind of things work. One of the very good feedback that we got for the first paper, besides this is completely crazy and I'm kidding, it was like, in the initial paper, we only vary 4 astrophysical parameters, 2 for supernova feedback and 2 for agent feedback. And they told us that maybe if you have a much larger parameter space, maybe there will be some degeneracies and this result will not hold anymore. So then we did this, and now we have run 2,000 simulations with the illustrious TNG model, and now we vary 5 cosmological parameters: omega mater, omega baryon, H, NS, sigma 8, but also pretty much all the astrophysical parameters that there are in these codes. These are the names. To be honest, I have no idea of what most of these things are, but these are phenomenological parameters describing some part of the astrophysics. And we have repeat the exercise and see, given all these changes now in feedback, are you able to really constrain anything at all? So we have repeat the exercise, and the answer, this is still preliminary, I haven't published this, but so the answer is yes. We can maybe surprisingly still constrain parameters, and now we can even constrain 4 parameters. So one of them is omega mater. The second one is the ratio of omega mater over omega baryon, which is something that initially we thought that this was really the quantity that we will be measuring, but it seems that these two is something that we can measure. We can measure H, and I have some ideas of why this will be possible. And we also measure like the IMF. So the IMF is something that the galaxy formation is kind of important, and this is a parameter in our astrophysics. Basically, tells how many. It basically tells you the slope of how many, let's say, massive stars you form. So this is one example of how things look like when you do this likelihood-free inference. This is now learning the full posterior with all these parameters. So for instance, this is H. Constraints on H are not particularly good, but again, this is like one galaxy. IMF, and also this omega mater and this ratio. Let me very briefly mention this. So Chan, who is a postdoc at Princeton, is amazing, really amazing researcher, has now applied this to real data, and this is something that will appear next week on the archive. Really bring this idea to real data. So the idea here was basically, that in the first paper we use galaxy properties, things like stellar mass, stellar metallicity. These are things that we don't really measure. What we really measure are things like the photometry. So what Chan has done is, taking the illustrious TNG model and do a forward pass where you basically model the photometry of each galaxy, taking into account not only the change in astrophysics, but things like the dust, the noise in photometry and all these things. And then using normalizing flows, he was able to compute, to estimate what will be the probability of having some cosmological parameters given your photometry. If you do this with one galaxy, this is what you get. It doesn't work. And maybe it's expected. This is photometry. We're really losing information by doing this. But you can also do the same exercise for now a population of galaxies. You don't have to restrict yourself to one single galaxy. And the expression for this is basically this, and these are the results. So this is omega mater, sigma 8. These are constraints. Let me emphasize, these are constraints coming from 22,000 galaxies. There is no clustering here. This is only coming from photometry. This is basically telling us that there is some cosmological information just on galaxy properties. So this will be on the archive next week. And yeah. Let me just advertise a few things. If you are working on machine learning and you need data to train your model, where can you find the data? So, in New York, we really have gigantic things. So, if you are working with M-body simulations, just keep in mind that, we have, like, I don't remember, but I think it's close to 50,000 M-body simulation. Again, this is the largest set ever run, varying lambda cold dark matter, W, massive neutrinos, varying the DC mode, primordial non-Gaussianities, even now recently with this parity odd population with William Coulton and and Oribel Fircox, and now we are also about to finish with modified gravity. Everything public available, more than 1 petabyte. You don't need to download a single byte. You can just go to our server in New York, and you will have one core to analyze all the data there. Most of the data in Camos is also public available, the same thing, maybe 1 petabyte of data, but you can just go to our server in New York and you can just analyze everything there. If you are familiar with things like the NNIS dataset, which is the most kind of basic, let's say, dataset in let's say machine learning, we have something very similar in cosmology, which is a collection of thousands, hundreds of thousands of 2D images, 3D grids, run illustrious CNG, but in cosmology, but in astrophysics, different codes. Again, everything public available. This is only 70 terabytes. This is much more handy. And then finally, if you are interested in working with semi-analytic models, we also have a lot of different things, a lot of teams with different models. And I want to probably conclude here. And thank you very much.
Thank you very much, Paco, for the great talk. So we have time for questions.
Thank you for the great talk. So I have a couple of very quick questions. So the first one is, can you discuss a bit how or if the loss function affects such kind of analysis? Because you never mentioned like the choice of the loss function.
Oh, very nice, very nice. You mean like for the graph, for instance?
Yeah, yeah.
Exactly. So, I mean, if you do, for instance, parameter, if you do regression, then you can use the mean square error or the root mean square error or the L1, all these kind of things. When you do likelihood free inference, the loss function is really, I mean, you don't really have a lot of freedom there. In our case, we estimate for the first thing, the posterior mean and the standard deviation of the posterior, the loss function is given. You cannot really play with that. And when you do the normalizing flows, learning the full posterior is basically the same thing. You don't have freedom in that case. When you do regression, yes, but for inference, in general, no.
Okay, thank you. And the second question is a bit selfish, but what is the FOVR model that you are using for the simulations, and what are the priors in the parameters of the model?
Very good. So this is like the UAM-CSIC. So for this parameter, if I remember correctly, we go to from 10 to the minus 7, I think, to 10 to the minus 4. That is already ruled out, but we say that, I believe, or 10 to the minus 3. I don't remember, but yeah.
Okay. Okay. I think everything looks good, except that when you, I think there's a philosophy to do things faster, to get faster analysis and get a tighter concern omega matter. But in all these things, a model is assumed, right? And let's not forget that the matter density of universe to be 0.28 or 0.3. It's not that important unless it is degenerate with the properties of dark energy, right? So as a theoretical physicist, from theoretical physics point of view, it's important if it is, for example, lambda or evolving dark energy. So when we deal with the actual universe, right, and it's an unknown, background expansion. So it's very important to not to get confused when we train all the, machinery based on a particular model can affect a misunderstanding.
Exactly. I completely agree with this. For CAMOS, galaxy formation, the uncertainty index are gigantic. So that's why we use all these different models. But, for things like cosmology, or, if there is something that you have really missed in your model, all these kind of things is going to give you like an answer, right? And it's like, how much can I trust this? So for these kind of things, there are things like anomaly detection, or, there are ways to even compute the evidence with all these methods that is going to tell you, how much really do you can trust this model. Given this model, you get this result, but what is really the evidence of this model? So there are techniques to do this. And of course, you can try to also look for anomalies to see if there is something that your model cannot explain. But it's a very good point.
Hi, thanks for the nice talk. So I have actually a couple of fundamental questions. So regarding your curvature simulation, is it valid for relativistic assumption? Here I am.
Oh, sorry.
Is your curvature simulation valid for relativistic assumption?
You mean like relativistic effects?
Yes.
So that's a good question. So, I mean, for the hydro, these are super small boxes, 25 megaparsec. So I don't think this will really have any effect. For them body, as far as I know, as long as you are within lambda polar matter, you are fine. For things like, yeah, modify gravity, probably not. And that's a good point. Yeah. So this is maybe something.
Okay, thanks. Again, is it possible to maintain FNL parameter in your simulation? And if so, can you, run your simulation for different FNL parameter and then later calculate the properties? I mean, the cosmological properties like power spectra, bispectra.
Not sure if I understand. So you're talking about FNL, so the planetary
Yes.
non-Gaussianities, and
Yes.
your question, can you repeat, sorry?
So is it possible to run the simulation for different FNL and then, yeah.
Exactly. So what we have for FNL is like a lot of simulation with a fixed value, but we also have these Latin hypercubes where what you do is basically to vary this parameter, like, 1,000 times.
Okay.
So we already have all these things. And
Okay, thanks. And last one, I think you use the Pylians to maintain, to find the void catalogs. Yeah, thanks.
yes, I wrote that, but there are also, I have some colleagues that use BIDE, and it's always like a.
Okay. Thank you.
Hi, a question up here.
Oh.
So a pessimist's view would be that after you, even when you work at the field level, after you marginalize over astrophysical uncertainty, you are only collecting data from linear and mildly nonlinear scales, where power spectrum and perhaps bispectrum are good summary statistics that almost gets you all of the information. I wanted to understand this, if within this analysis at the field level, you see any hints of collecting more information and doing better than just the standard summary statistics.
That's a very good question. So yeah, so the typical thing that we do for this is you compute the power spectrum, for instance, directly from this. And what we find is that with the power spectrum, you don't gain as much information. And I think regarding the first question, whether this might be just coming from power spectrum and bispectrum. So the way that we construct the graph is that basically, you link two galaxies if they are within a given distance. And this distance is a hyperparameter. So the model will choose what is kind of the optimal distance. So I have the feeling that, if the model were using really like large scales, it will have preferred a graph where everything will be connected. Because right now, there is not really way to go to transmit information from this galaxy to that one, only until the very end. So the clustering between these two galaxies in this particular graph is not considered. So my interpretation of this is that the graph is actually extracting information from much smaller scales. It really prefers to go there.
So, but there is a standard way to check. You just take the same information and you run a standard 2- and 3-point function with all cross correlation, and you compare the error bars.
Exactly.
Did you do that? Is there a comparison?
We did this for the power spectrum, not for the bispectrum.
I see.
And for the power spectrum, you get worse results.
Oh, because usually there are degeneracies, and with the bispectrum, you can resolve many of those degeneracies. So that's the standard expectation.
That's a good point. That's a good point. It would be nice maybe to check. But I mean, looking at the formula, maybe you understand this better. But to me, this doesn't look like some power spectrum or bispectrum.
Well, I think the question is not what it looks like, but whether it can do better. And so to convince oneself, you want to have like an apple-to-apple comparison, same data set, to analysis, and show that the error bars are favorable.
Yeah, that's completely fair. Yeah, we need to do for the
very interesting, though. I mean, I really like the approach. Thanks.
Hello. Hi. Hi. Yours was an amazing talk, and like there's a lot of amazing work that you've presented today. So I had a couple of questions, which are like very naive questions. One was regarding so the graph neural networks that you're using, is there any convolutional neural network involved in this?
Exactly. So graph neural networks are, you can be seeing this as a generalization of CNNs. So no, there is no CNNs for this thing at all. Graph neural network, you should think about this like a CNN where you can work with really irregular and sparse data. But this is a completely different technique. No CNNs here.
So actually, I think there is a software which was I mean, this code is probably written by Perrodin et al, which is called DeepSphere. Apparently, it's used for the CMB. So there apparently they have convolutions within the graph neural networks. If you are aware of it, like If you could
yes.
comment on the differences between that kind of neural network and the ones that you have employed.
Yes. Okay. So I'm not sure about this, but the only problem with graph neural networks is that if you cannot right now work with 1 million points, if you have 1 million points and you put all this connection, it will not fit in the memory of the GPU. So we are really limited to maybe using 1,000 galaxies. So people in machine learning has created all these hierarchical graph neural networks that is probably related to maybe what you are mentioning, where you really have this thing and you can even put this on a regular grid and use maybe CNNs and all these things.
And like regarding the error estimation that you've said, like it's like how exactly are you doing it? Like estimating the like the sigmas or the standard deviations?
Yes. So for this first case, we use this thing that is called moment network. So if you train a neural network and you use the root mean square error, it can be shown mathematically that what you are really doing is computing the posterior mean without making any assumption about the posterior. So it can be shown that if you add another term to the loss, you can compute like the standard deviation of the posterior.
Is it something to do with the heteroscedastic loss function or something like that? There's a heteroscedastic loss function where we actually estimate the sigmas as well. Like, is it similar to what?
Exactly. There is another term in the loss function,
right,
that is a quadratic term. And
right. Okay.
Exactly.
Okay. Thank you.
More question? Okay.
So maybe related to a slightly earlier question, I see that in these Quichot simulations, you have a few parameters outside standard lambda CDM. Are you planning to include more of these types of beyond standard lambda CDM models, such as like power spectrum with a cutoff or exotic energy injections or these sorts of things?
If you think that it will be interesting, this thing, we can think. I mean, the problem is the system administrator. You know, it's like this fucking Paco running more simulation, more and more. So sometimes you really need to justify. And if it's something very exotic, they may say, but in principle, yes.
More questions?
So when you do cosmology with photometry, what do you use for photometry? Because you can use a number, you can use several numbers for different bands.
Oh,
you
yeah,
can use profiles, you can use pixel level photometry.
Yeah, no, this was only the luminosity in the SDSS bands.
Okay, so 5 numbers.
5 numbers.
So great talk, Paco. So I have a question. Usually when I'm doing simulations, you spend a lot of time trying to understand which is the box size you need to use, the resolution you need to use. So you tested how you cross-tested different hydro simulations, one or the other. Does it also work if you change a lot the box size and resolution? Does machine learning, is it robust to these things?
Yes, very good question. I forgot about this. So the answer is yes. We test these, all these simulations have more or less roughly the same resolution. The RANSYS and ENFO are a little bit different. But we also test this with a higher resolution hydrodynamical simulation from the Illustris CNG. It works. And we also even changed the halo finder because, as you know, this thing could also, and it still works. So that's why, you know, this is incredibly robust. Thank you.
One last question maybe over there.
Thanks, Paco. Great talk. Just to maybe come back to the questions about the power spectrum. So you mentioned that here you're using peculiar velocities, and then when you don't use them, you don't gain much. So we're not going to be seeing peculiar velocities, right? So
very good question, Andrei. So it's not that you don't gain so much; it's that it directly doesn't work. If you train on Illustris, doesn't work on Simba. We are thinking about this, and probably maybe we will solve it. But I mean, we have peculiar velocity surface. And you have an estimate of the peculiar velocity. So, I don't think it's impossible. We actually are working on this. And even this thing, if you have uncertainties in the peculiar velocities or the distances to the galaxies, it still works. You lose on accuracy, but it still works. But this is a very good point.
So I'm going to ask you the last question myself. So you were talking about this graph neural nets and all that. So I was just curious, at the moment you are doing everything in real space.
Yes.
If you go to, like, I don't know, Fourier space or something, can you still apply something similar there? I don't know if you gain anything, but it doesn't even make any sense. But in principle, you have a graph there, right? It could be fine. Something, I don't know how exactly it works, but I'm just curious if by going to another space, things might be different or better, or Because then you have control over modes, which modes you're exactly talking about, stuff like that.
That's a good point.
That's the question.
But you mean, like,
I mean, for example, I don't know, taking FFT, go to free space of this quality simulation, right?
but in this case, you mean with a grid or with the points?
Let's say with the points, and then you will have your galaxy catalog in the other space with a K vector, and then apply graph neural net there. I don't know, maybe it doesn't make any sense. I'm just
No, that's a good idea. I think in principle should be possible. The only thing is that in Fourier space, translational invariant is always a little bit, I believe, difficult, right?
Yeah. There are things like that that one should be careful about.
Yeah, but it would be nice to maybe try.
Okay. Thanks a lot. Actually, we need to finish.
Thank you.
Last question. So let's time Paco again.
Thank you.
So we'll be back at in maybe 11:30. Yeah. Okay. Sorry.
I understand Spanish. Oh, yeah, sorry, man. Yeah, yeah. Actually, yeah, I don't have a comment about take galaxy classes. Sounds still but we're not aware. Yeah. And those that we can yeah. So that it could be like something like so yeah. But okay, just my idea. No, no, no. Well, yeah, yes, that idea. But the first thing I'm reminding is okay, not very fast. But that's what it's not. Now, la más
How are you, man? Nice to see you. Yeah. So let me just connect this. No. Let's talk. So at the end, they didn't give you this. No, I mean that was long shot anyway because. So I agree with the review actually because I did write things out of my team. I mean, I have been in this kind of things. I don't know. No, so the trick is write what they want to do, whatever you want. That's true. I mean, but do you know or can you know who is in the committee? Okay. If I can write a message what now I for a day. I mean that was my question. Well, there is the overall the then to the that is the point. That's
it's working, but it's a pain in the ass. Okay, we are ready. And do you have the PDF? Yes. Okay, now, can you send it to Cosmo 23? At the Cosmo 23 Madrid? Yeah, and no. Cosmo 23. Okay. It's the email that you sent me. Yeah. Yes.
Yeah.
Yeah, the lights are up there in the corner. Emilio or Antonio, someone tell them that what to do is around. Okay, you don't have to do that. Okay, let me do that in a minute, or we're starting at half past, right?
Hey, welcome everybody back to the last plenary session. Okay, it's a pleasure to introduce Eleonora Valentina, talking about interstitiation, the standard plan CDA. Thank you very much.
Thank you. Thanks a lot for inviting me here, this great conference. Okay, so let me start by introducing the lambda Godard matter model that has been chosen the standard model in cosmology mainly for its simplicity, but is based on three completely unknown quantities that are inflation, dark matter, and dark energy. And for these three completely unknown quantities, we choose the simplest possibilities. So the inflation is given by singles roll the scalar field, the dark matter is cold and pressureless, and the dark energy is just a cosmological constant term. So there are theoretical shortcomings for this lambda Godard matter model, and this seems more an approximation of an underlying physical theory yet to be discovered. For this reason, we expect in some sense deviations from the model if we with increase of the experimental sensitivity. And now that we start to see discrepancies between the values of certain parameters coming from different experiments, this could indicate a failure of the canonical lambda Godard matter model. So the H-naught tension is the most statistically significant lasting tension, and is the 5 sigma discrepancy between the value measured by the choose collaboration using a distance ladder and the value estimated by the Planck collaboration assuming a lambda Godard matter model. So on one side we have distance ladder. This means only geometrical quantities. The CFAs in this case are calibrated with parallaxes, detached eclipsing binaries and masers. Then the CFAs are used to calibrate the type 1a supernovae in nearby galaxies, and the most far away type 1a supernovae are used for the Hubble flow. So now they can reach such an amazing constraint on the Hubble constant because they are performing fit for the three ranks at the same time using also the off-diagonal terms. And now, and for this reason, the tension has reached the level of 5.7 sigma. On the other side, we have instead the CMB constraints. What does it mean? That we are measuring something in the early universe, then we assume a model for the expansion history of the universe, and we estimate the value of the Hubble constant today. So we have the map of the CMB anisotropies. We expand the Legendre polynomial, the 2-point correlation function between the difference of temperature and two direction in the sky. We obtain the temperature power spectrum. Here we can see an amazing agreement between the theoretical model, that is the blue line, and the data, that are the red dots. But how is this agreement obtained? Okay, we have to assume a cosmological model, the lambda Godard matter model, and we vary the parameters, and we can see that the effect is mainly a shift of the peaks and a change in the amplitude. So what we do is to find the best combination of the parameters that can best fit the data, and we do this using a Bayesian approach and MC codes. In this way, we obtain the constraints on the parameters that we well know that are, for example, we have many sigma indication for a cold dark matter different from 0. We have the scalar spectral index is almost 1, but not exactly 1 as expected for the dynamics of the infraton field. So this is a wonderful confirmation of the standard model, but we have to take into account that this is model dependent. So if we change the model, our results can be completely different. And then there are degeneracies between the parameters that can bias the final results. Just to give an example, okay, these are very different cosmological models with different cold dark matter density, curvature of the universe, and values of the Hubble constant. And by eye, you can see that they are very similar. So the fact that the temperature power spectrum in general, the CMB, is sensitive to the parameters doesn't mean that can really detect them if you don't assume the model that you want to test. So now we call the Hubble constant tension the tension between these two measurements, but are there any other H-naught estimates? Yes, there are many. So we have the indirect estimates that are CMB, and they are more in agreement with the Planck result. And then we have the direct estimates in the late universe that are instead in agreement with the choose value. So on one side, there are the ground-based CMB telescope, and this is ACT and SPT, and both of them are lambda Godard matter model dependent. But on the same side, we also find the spectroscopic surveys for BAO and full shape for BOSS and DBOSS, And you can see that they all agree very well on a lower value for the Hubble constant, and they all agree with the Planck result. But we have to be careful because also these results are lambda Godard matter dependent. On the late universe side, we have not only the supernovae, the type 1A supernovae calibrated with the Cepheids, that are the shoes measurements, but we can also calibrate the type 1A supernovae with the tip of the Reggian branch, that is the peak of brightness reached by the Reggian stars after they stop using hydrogen and begin fusing helium in their core. And usually we talk about the Friedman measurement that is here, and because this is in agreement at 1.5 sigma with both the Planck result and the shoes value. But since the Friedman measurement that is now 2 years ago, we had many new measurements, and these came out this year, Skolnick et al. And Anderson et al. You can see that they are very much in agreement with the shoes value. Then we can calibrate the type 1A supernova Miras that are variable Reggian stars. Then we have the Megamaster Cosmology project. In this case, there is no distance ladder, so these are used directly for the Hubble flow, and these are very much in agreement with the shoes value. So this is completely independent from all the other experiments. Then we can use the Tully-Fisher relationship, and again, this can be calibrated with Cepheids and TRGB, and this is giving a much higher value for the Hubble constant. We can use the surface brightness fluctuation. In this case, if this is considered as the long range indicator in the third rank, this can be calibrated again with both Cepheids and TRGB, and is giving exactly the same value as shoes. And then we can have the type 2 supernovae that can be used as standardizable candles, and you can see they also agree very well. So just saying that the tension, the Hubble constant tension is between shoes and Planck is reductive. There are many other measurements, and if we average them all together, the tension is at the level of 6.4 sigma. If we do a jackknife of the results, so we remove one group of measurement per time, and we average the others, and then we choose the one with the largest error bar. This is, of course, when we remove the shoes measurement, we see that the tension is still at the level of 5.3 sigma. If we remove two groups of measurements, and so we remove the shoes measurement, but also the TRGB, the tension is still at the level of 5 sigma. So this tension is very robust. It doesn't really depend on just one experiment, tool, method, groups that is analyzing the data. At this point, okay, has been discussed this plot in the Friedman review because it seems that the Hubble constant measurements in the last 40 years are converging to something. But what is missing here is a measurement of what has been measured by what, because at the beginning the tension was between the same kind of measurement at the same redshift, while now the interesting thing is that there are no late universe measurements that are below the early universe measurements, and vice versa. So if we have a true value, we expect a scatter around this true value, but this is not what we see. We see a scatter here, we see a scatter here, but we don't have any late time measurements that are below the indirect ones. So at this point, a single error in one of the experiments is not enough. The tension is still there. We can have multiple systematic errors in the different experiments, but they should bias the measurements all in the same direction. The simplest possibility is that we are using the wrong model to analyze the data, and because the measurements that are giving a lower value for the Hubble constant, they are all assuming the same model, that is the lambda Godard matter model. So let's try to modify the lambda Godard matter model and see if we can solve the tension easily. So the simplest possibility is, of course, considering an effective number of relativistic degrees of freedom recombination. So we want to modify one of the pillars of the lambda Godard matter model, that is the dark matter sector. And in this way, we are modifying the expansion history before recombination. So we call this class of solutions early time solutions. We want to play with this strong correlation that we have between the neutrino effective number and the Hubble constant. So in order to be in agreement with the shoes measurement, we should be here. That means an effective equal 4, and this is allowed now at 6 sigma by Planck. So this is not anymore a solution. Even if we let an effective free to vary, H naught is very low. So the tension can't be solved with additional degrees of freedom at recombination. Another possibility is to change the second pillar, that is the dark energy sector. In this case, we want to replace the cosmological constant with a dark energy that has an equation of state free to vary. Here we can completely solve the double constant tension with a phantom dark energy. Phantom dark energy means a lot of theoretical problems because it violates the low energy condition. We call this class of models late time solutions because in this case we are modifying the expansion history after recombination. So if we now consider the formally successful model in solving H0, so what we are doing is assuming a different expansion history, analyze the CMB data only, in this case the Planck only data, and obtain the constraints on the parameters, look at the phase value of H0 comparing with shoes. We see that there are models that can solve completely the tension below 1 sigma, and these are mostly late time solutions. So here we don't have a model comparison, so we are not seeing if this is also producing a better fit of the data. The problem is that as soon as you include the late, so you have the low redshift data like BAO and supernovae, these kind of models are excluded. Here I'm showing you the phantom dark energy case. Okay, this is Planck only. This is introducing the BAO data. You see that you are back in agreement with the cosmological constant. And if you compare the best fit from Planck, that is the dashed line, and from Planck plus BAO, when the equation of state is free to vary, you see that they are completely different. And the phantom value preferred by Planck is very much in disagreement with all the BAO measurements. So the problem when we have the late universe measurements is that we are failing in recovering the shape of H of Z at low redshift. So we have the fourth complication when we try to solve the double constant tension is that we call the sound horizon problem. In a few words, when we combine BAO and Pantheon, we are measuring this green region here. So in order to be in agreement with a higher value for the Hubble constant, we need a lower value for the sound horizon. And if we are in agreement with Planck, we have instead a lower value for the Hubble constant and a higher value for the sound horizon. So something like a late time solution that is a phantom dark energy, but also the phenomenological emergent dark energy that I showed before, is moving along this line here, so can increase the Hubble constant without problems, but can't decrease the sound horizon. So these late time solutions are always in disagreement with the BAO data. So we need something like an early time solution that is moving along this line of correlation. And this class of models, we have early dark energy and the neutrino effect in number. But as you can see, the best fit of these models is always around the lambda Godel matter model. So we solve the tension not because we have a strong overlap, but because we have a volume effect. So we increase the error bars, and now we alleviate the Hubble tension. But if we don't add a prior on H0 that is forcing the Hubble constant to be more in agreement with shoes, we see that the model is always preferring the value for the lambda Godel matter model. So what is the early dark energy? The early dark energy is a new fundamental scalar field that is accelerating the expansion history before recombination, is about 10–12% total energy density. Since we want the right amount of reduction of the sound horizon, we need a mass around 10⁻27 eV. So what the first proposal has been an axion early dark energy with this potential, but an axion doesn't really work because we need an equation of state equals 0, and this is a disagreement with the late universe. So we need something that can redshift away much quicker than radiation, and this so we usually n should be larger than 2, but we fix this to 3 in the data analysis. So these are the constraints for the early dark energy from Planck. And you can see, okay, these are 3 additional parameters. You can see that the fraction of early dark energy is in agreement with 0, and the Hubble constant tension is very low. So the early dark energy is not working with Planck and is not solving the Hubble constant tension unless we are adding a prior on the Hubble constant. Okay, so now if we do the same as before, so we want to classify the formally successful model that can solve H0. In this case, we are not looking just at Planck, but we are also adding BAO data, supernovae data, cosmic chronometers, as priors on the Hubble constant. We see that the models that can solve the tension now are mostly early solutions, so modification that before recombination. Here again, we don't have a model comparison, so most of these models are dispowered by chi-square analysis. So now we have an additional complication. The early solutions that are proposed to alleviate the Hubble constant tension are increasing the S8 tension, where S8 is defined as the combination, the clustering parameter and the matter density, and is used to quantify the tension we see in this plane, sigma 8 omega matter. So here, for example, we have a combination of kids Viking 450 and Boss, and you see that this is 3.4 sigma disagreement with the Planck value. We have 3.1 sigma disagreement with kids 1000 alone, 2.5 sigma for the dark energy survey Y3, 2 sigma for HSC Y3, and here we can see that actually the dark energy survey and kids are overlapping exactly perfectly well. So the fact that they are showing a different tension with Planck is because they're using different tools. For kids, they're just looking at the value of S8. For the dark energy survey, they're using the suspiciousness statistics, so considering the whole volume of the parameter space. But again, what is really important and interesting, in my opinion, is that we have the same behavior as for the Hubble constant tension. So in this case, the early universe measurements that are CMB are preferring an Eichel value for S8, while all of the late universe measurements that are not only weak lengths, but also cluster counts, galaxy clustering, redshift space distortion, they're all preferring a lower value for this parameter. So now what is the problem with the models that can solve the H0 tension? Okay, we saw this plot before. So we want to be here in agreement with an Eichel value for H0, at the same time a lower value for the sound horizon to solve the Hubble constant tension. But if we do so, we are moving along this line of correlations that are valid for the CMB experiments. So if we are here, we are in agreement with the green line. That means a much higher value for omega m h square. And this kind of models correspond to this green region here. So if you want to be in to reduce the sound horizon, increase the Hubble constant tension, you are at the same time increasing this omega m h square, so you are exacerbating the S8 tension. So this kind of solutions don't work with the weak lensing data. So every time we are looking for a solution, we shouldn't just consider the Hubble constant and the sound horizon, but also the matter density at the same time. So if we do so, this is the density of the proposed cosmological models, now 2 years old. Here we have 180 models. The model proposed were in this review more than 300, but most of them didn't have an analysis. So these are the models that we can put in this plane. And if we want to be in agreement with all the data sets we have, the point should be in this intersection here and here. And this is not happening for any of the model proposed. Since then, at least now we have 500 models, okay, but at the moment there are no specific proposals that are likely or far better than all the others. So let me show you a few examples. We have the interacting dark energy dark matter model. In this case, we are modifying the conservation equations, introducing an interaction rate Q that is proportional to the dark energy density, the conformal rate via this Xi that is quantifying the strength of the coupling. It should be a negative parameter. So if we assume a model like that, we have that the Hubble constant tension, the Hubble constant value is exactly the value measured by shoes. In this case, okay, we have just an upper limit for the cold dark matter density. Why this is happening? Because from the CMB, we can measure accurately well this product here, omega m square, from the tree structure. So if we have this flux of energy from dark matter to dark energy, we have less dark matter in the universe. So we are naturally obtaining an Eichel value for H0. So now if we add a prior on the Hubble constant like the shoes one, we have 5 sigma standard deviation indication for a coupling between dark matter and dark energy. And in this case, the sigma 8 tension, the S8 tension is not defined because from Planck alone, we have this red region here. So the constraints are very relaxed and are also shift in agreement with the dark energy survey. So there is not a S8 tension for this model. So now we want to ask, okay, but is this producing a better fit of the data? So to do so, we use the Bayesian evidence. The Bayesian evidence is based on the Occam's razor principle. So if we have additional parameters and for this model to be favored, we need a significant improvement of the fit of the data. So we can compute these with the bias factor and we can compare with the revised Jeffrey scale. So we have a weak, moderate, or strong evidence for model 0 against model 1 if the bias factor is greater than 1, 2.5, or 5. So if we do this for the interacting dark energy model, we see that from Planck alone, we have a weak evidence. So we are improving the fit of the data. And if we add a prior on shoes, we have a strong evidence for the interacting dark energy model. Okay, so we can say we found the solution. But here, there is an additional complication of testing of this extension of the standard model, that we can have, because of the correlation, a fake detection for something that is not real. In this case, we produced mock data sets, in this case, Planck-like data, and assuming that there is no interaction between dark matter and dark energy, and then we let this interaction free to vary, this parameter free to vary, and we see that we have more than 3 sigma evidence for an interaction that is not in the fiducial value. And this is because the posterior is skewed towards negative values. This is just due to the correlation between the parameters. So every time we look at a model, we should always test with simulations if these results is reliable or not. So what we can do is, okay, this is a mock BAO data, add experiments, break the correlation. In this case, we have just a lower limit for Xi as expected. So what happens when we add the real BAO data to the real Planck data? We have just one sigma indication for a coupling different from 0, but a higher value for the Hubble constant, alleviating the tension at the level of 2.1 sigma. Now, here it's difficult to understand if this is a residual tension or statistical fluctuation, because BAO data are formed in the early universe, but we're measuring them in the distribution of galaxies. And in many points of the data reduction point, we are assuming a model. The model we assume is always the lambda Godel matter model. So instead, we try to, instead of using the 3D BAO data where we are reconstructing the Markov distance from the redshift, to use the 2D BAO measurements, this is just the angular distribution, to see if this is changing something in our results. So if we do, if we instead of using the 3D BAO data, we use the 2D BAO data, BAO transversal, assuming a lambda Godel matter model, we see that they are very in agreement with each other. But if we do the same for the interacting dark energy model, you see that the angular BAO are giving H0 equals 75. So we are completely in agreement with the value obtained by the shoes measurement. So we can add a prior on shoes, and we have again more than 5 sigma indication for a coupling different from 0. So in this case, here we are using this BAO transversal that has been derived by the National Observatory in Brazil. So you can say, okay, these are very old data. In one case, you have the BOS and the BOS data. In the other case, these are obtained in a completely different way. So we redid the analysis, replacing the 3D BAO data with the 2D BAO data derived by Menot and Marra in this paper. They are completely exactly the same, BOS DR12 and the BOS DR16. And okay, these you see that are completely, they give exactly the same value for the Hubble constant for the lambda Godel matter model. But as soon as we switch to the interacting dark energy scenario, this is what we have for the 3D BAO, and this is what we have with the 2D BAO. So there is a shift more than 1 sigma for the Hubble constant, and again, 1 sigma indication for the interacting dark energy. So what I want to argue is that we have to be very careful using the BAO data in extended cosmology, especially if they are very different from the lambda Godel matter model. And in my opinion, this BAO data should be revised in non-trivial manner when we extended the cosmology. So just using the BAO as they are and ruling out all of the late time solutions because they are in disagreement with the BAO, okay, we should be just careful. So now let's go back to the CMB data. Because I told you that Planck has a problem of the correlation between the parameters. So we wanted to test with the new ground-based telescope. In this case, okay, we use Planck, but we are also using the ACT data. The ACT data, okay, the Planck goes from multiple 2 to 2,500, ACT from 650 to 4,000, more or less. So these in the ACT data are missing the first 2 peaks, and we want to use something here again to break the correlation, so we can use the WMAP data that are arriving up to multiple 1,000, or we can replace these first 2 peaks, cutting the Planck data up to 650, and this is the last column. So what we see is that all of the CMB data, all of the CMB experiments are very in agreement with the same value for decoupling and the Hubble constant. So this result is robust. We have more than, for some of the combination, more than 2 sigma indication for a coupling different from 0. And this result is coming from the high multiples, where, okay, this is the log scales, so this error bars seem very large, but they are actually very, very small, so they weight a lot. So because of these higher multiples, we are breaking the correlation. So now this result is not anymore due to okay, there is not anymore a fake detection, but is a true feature of the data. So let's see another example of late time. We introduce this omnipotent dark energy, that is a dark energy that can have a negative and positive energy density, and an equation of state that is quintessence of phantom in at least 1 point in its parameter space. So these can incorporate oscillatory non-monatomic evolution and can have singularities, phantom divide line crossing. One simple, the simplest model that can have an omnipotent behavior is a Taylor expansion of the dark energy density around the AM. Okay, here we introduce this model. We analyze this with the CMB data and other combinations, and we can see that we can solve the H0 tension without any problems if we have a phantom crossing, and a phantom crossing of more than 2 sigma. And this is a recent paper when we are using also the new data from Pantheon Plus and SHOES and BAO, and you see that we can obtain a negative value for H0. This is happening because in this case we have a negative dark energy density. So every time we rule out again the dark energy solutions at late time, if they have a negative dark energy, they could be in agreement with the data and solve the Hubble constant tension. So you can see they are also producing a better fit of the BAO data. This is for the phantom crossing, and this is for the lambda Godard matter model, and this is for the full combination of data sets we have. So the lambda Godard matter model is the dashed line, and this phantom crossing is performing better in recovering the BAO data. So this has been analyzed also independently by this other team, and you can see that not only can solve the Hubble constant tension, but also reducing the S8 tension. Okay, so now I'm talking about this tension, but is this a real tension? Because there is an excess of lensing in Planck, so everybody knows the A-lens problem. So we are introducing this lensing amplitude, and we expect this to be equal 1 from general relativity, but Planck is measuring a lens larger than 1 at 2.8 sigma. This is not a true measurement of the lensing that can be done by the reconstruction, the lensing reconstruction, for which a lens is exactly 1. So this is improving the chi-square of about 910 with just 1 additional degree of freedom. So if we vary A lens, we see that we have a strong correlation with S8. So if A lens is really equal 1.2, we don't have any S8 tension at all. So it could be that Planck has a systematic, and that is this excess of lensing that is A lens. So if we marginalize over A lens, there is no more the S8 tension. And what about the other CMB experiment? SPT3G is completely in agreement with the weak lensing data, and also ACT, the error bars are so large that the tension is very much reduced. And now there is the new release together with the dark energy survey KIDS 1000, and the tension is at the level of 1.7 sigma. Marika showed this in a talk. So now, okay, it could be that there is a systematic in Planck, so there is not a safe tension, but it could be also that this is an indication for something for new physics. So assuming general relativity, is there a physical explanation for a lens? Yes, and this is a curvature different from zero. And in particular, so if we fix a flat universe omega k exactly to zero, we have this more than 2 sigma evidence for a lens different from 1, but a lens can be 1 as predicted by the general relativity if omega k is less than 0. Okay, so now we have to be careful again because these are not the same kind of parameter. On one side, we have a phenomenological parameter, a consistency check that has been introduced and that Planck is failing. On the other side, we have the omega k that is predicted by the general relativity, so is not a parameter beyond the standard model. This indication for a curvature different from 0 is in the Planck paper at the level of 3.4 sigma. And so we can ask, okay, but maybe this is due to the geometrical degeneracy, because we saw before that if we, because of the correlation, we can have a skewed posteriors toward negative values for decoupling. So we simulated a Planck experiment that is this blue line, assuming a flat universe, and you see that we can recover omega k equals 0 with a 2% uncertainty. So this is not due to the geometrical degeneracy, and is producing an improvement of the fit of 11 with just one additional degree of freedom. And this is doing better than A lens parameter because it's not only fitting better the damping tail, but also recovering the low anisotropy quadrupole present in Planck that was already present in WMAP and was explained by Stadio in 23 with a closed universe. So this is a feature that is present in all the CMB data. So now what is the problem? The problem is that when we combine again with BAO, we have exactly a flat universe. So in my opinion, the question we should ask if we can do this combination, because if this was the opposite, so we had from Planck a completely flat universe, we were adding the BAO data, we were obtaining an evidence for a closed universe, nobody would believe to that. So we believe strongly to these results because of our confirmation bias, we know, and we want the universe to be flat. So if we look at the consistency between the Planck data and the BAO data, assuming a flat universe, they are in amazing agreement. But if we do the same, letting the curvature free to vary, these are the Planck constraints, and these are the BAO data. They are far away, and they are all on the same side. So they are in disagreement. This is true also for Caspec. So combining these two datasets together, assuming letting the curvature free to vary and claiming that the universe is flat, is the same as combining together an Hubble constant prior when varying the neutrino effective number and claim that we have an evidence for a neutrino effective number equal 4 and a sterile neutrino. So we should be really careful in combining datasets that are in tension. This has been found independently, so there are more than 3 sigma tension by Handel in his paper, and it's true also for the full shape power spectrum that is the Fourier counterpart of the BAO data. So, as has been argued in this paper by Stefano et al., okay, we can't use the fact that we have very small omega k similar to 0 to just force omega k to be 0 and then forget that we can have a curvature. So since we are tensions between the parameters, the most simplest way to go should be consider at least 7 parameters, including the curvature, every time we do a fit of the data. But what happens if we do that? We are exacerbating all the tensions. So this is going in the opposite direction. For the Hubble constant, we found a value around 55. And for also in the plane sigma 8 omega matter, we are exacerbating the S8 tension. So omega k is behaving differently from a lens in this case. But what about the non-CMB data? If we take a combination of BAO, supernovae data, and BBN, they are preferring, again, a closed universe with a value of the Hubble constant that is in agreement we choose. And if we do an effective field theory or less structure to investigate the full shape data from both EBOS catalogs, removing the assumption of flatness from the beginning, the fiducial model, the covariance matrix, the reconstruction, we see that we have 2 sigma reference for a closed universe. If instead of considering omega k, we consider the physical quantity omega k combination with H, the evidence for a closed universe at the level of 4 sigma. And if we vary at the same time the equation of state, we have an evidence for a phantom closed universe at more than 99% confidence level. Okay, you see that this is Planck. So Planck not only is in agreement with a closed universe, but also with all the value of the Hubble constant. So there is no H0 tension at all. So in this case, it's difficult to understand if this is more or less theoretical convoluted than the lambda-Goddard-Matter model, because we were removing the fine-tuning of the cosmological constant, but we are introducing the fine-tuning of a slightly curved universe. Again, the only data in tension are the BO data. So is the universe closed? This recent paper from Statue and collaborators, where they claim that using the latest Planck PR4 and pipe CASPEC, we shift all the parameters completely in agreement with the lambda-Goddard-Matter model. But let's look this more in the detail. Okay, if we just look at the value obtained for the temperature power spectrum between the 2 release, this is the old one and this is the new one, you see that both A length and omega k don't change at all. So we have still A length larger than 1 and omega k larger than 0. And in particular, you see here, okay, the difference between the dashed and the black and the solid line is the difference between the 2 release. They are ruling out omega k equals 0 with the same probability. So they are not improving the consistency with the flat universe. What they are doing is changing the polarization. And so now what you have is the average effect that is pushing you towards the lambda-Goddard-Matter model. But at which price? First of all, we are introducing an internal inconsistency, okay, in the theta parameter. So this is shifting between the 2 release from here to here. The tension is at the level of 2.8 sigma between temperature and polarization, assuming a lambda-Goddard-Matter model, but much more than 3 when A length and omega k are free to vary. And we are producing a bad fit of the data. Okay, this is the reduced chi-square. Thank you. And you see that if we assume the best fit of the lambda-Goddard-Matter model, and you compute the reduced chi-square for the temperature and polarization data, the data are in disagreement at more than 4 sigma with the lambda-Goddard-Matter model. So it's true that with this new pipeline, we are very much more in agreement with the lambda-Goddard-Matter model, but we are doing this at the price of introducing internal inconsistency and producing a worse fit of the data. So now what about the alternatives in the experiments? For SPT, omega k is exactly 0 as well from ACT. And this is true also in extended cosmology. Okay, ACT, if we introduce extension in the neutrino sector, dark energy sector, inflationary sector, we see that this is always in agreement with omega k equals 0, while Planck is always preferring a closed universe. So we can say, okay, Planck is wrong. So let's go to using the ACT data. But the ACT data are giving you a value of the spectral index that is exactly 1. Exactly 1 means an Harrison-Zidovich power spectrum. So you have a 1 less degree of freedom. So this is powered for the Occam's razor principle. And this NS equal 1 is discovered by Planck at the level of 8 sigma. So the explanation in the ACT paper is that you can't break the correlation, you can't have a measurement of the spectral index because you don't have a measurement of the first 2 peaks of the CMB. So what we have done is to remove the first 2 peaks from Planck, taking just multiples larger than 650, and you can see that you can still measure NS less than 1 at about 4.3 sigma. So this is not the reason why NS is equal 1 in ACT. So what are the implications for the inflationary models? Okay, since you have this positive correlation between the spectral index and the number of V-foldings, from ACT, you are ruling out all the inflationary models at more than 95% confidence level. The inflationary models have single field that are the benchmark, so Starobinsky alpha tractor. So this means that the inflation, as we assume in the standard model, is ruled out by the ACT data. And this is because there is an inconsistency, okay, between Planck and ACT. This inconsistency is much more than 3 sigma if we add large-scale structure measurement as BAO and dark energy survey. And you see that also the direction of correlation is different between the two experiments. So now this inconsistency has been quantified, assuming the lambda-Godel-Matter model at the level of 2.6 sigma, or using the suspiciousness statistics. Okay, some of the parameters so can be in disagreement much more than 3 sigma, so this is considering the whole parameter space. And these are looking at the same observable and considering the same model, that is the lambda-Godel-Matter one. So what happens when we switch to consider extensions of the standard model? So we have this evidence for the early dark energy more than 3 sigma from ACT. That is valid also when we add the BAO data, but is completely ruled out by the Planck experiments. We have an evidence for a running of the running of the scalar spectral index at the level of 2.9, 2.7 sigma from ACT that is not present in Planck. And you have an evidence for a total neutrino mass different from 0 at the level of 2 sigma. From Planck, you have just an upper limit, and this is due to the strong measurement of the lensing, the excess of lensing that you have with the temperature power spectrum. But if you take, if you marginalize over the A lens parameter and you combine with the CMB lensing, you see that also from Planck, you have somewhat an indication for a total neutrino mass different from 0. So now we want to quantify the global CMB tension, trying to find an extension of the parameters that can solve this inconsistency between the CMB data. And we see that none of the classical extension can really solve this inconsistency below 2 sigma unless you don't have a neutrino effective number that should be less than 3. So if you rule out a third neutrino, you can have the 2 experiments in agreement again. So these are my conclusions. Given the quality of the data, I think that the problem is with our understanding of the universe, so the model that we are assuming to analyze the data. The problem is not just solving the constant tension, that is very easy, but at the same time, be careful with all these other additional complications, the sound horizon problem, the state tension, the correlation between the parameters and possible fake detection, the hidden model dependence of some of the data sets, such as BAO, the Planck lens problem, the inconsistency between the different CMB experiments. So this is presenting a serious limitation to the precision cosmology. This discordance, in my opinion, should call for new observations, stimulate investigation of alternative theoretical models and solutions. So I will leave you with this advertisement. We are working on that in Cosmoverse. It is a cost action, started 1 year ago. So you are welcome to join. There are 3 different working groups, and okay, so we hope to be able to solve the tension. Thank you so much.
Thanks, Eleonora. So, I mean, well, the very first figure of like all these measurements of H naught, like late time versus early time. So, I was wondering, I mean, I'm sorry to be like a little bit frank, but I think it's a bit misleading to say it's late time versus early time, because if you look at those measurements, except for the well, the exception of TRGB, which is actually fine in terms of Planck, the rest, there is one word that is repeated everywhere for all of them, which is Cepheids. Right?
That's not
they're basically I mean, you just mentioned calibrated by
that's
Cepheids.
not absolutely true.
So
here you have Cepheids,
right.
Here you have TRGB,
That's
here you have Miras that are not Cepheids.
I mean, you have these things that's calibrated with Cepheid, calibrated with Cepheid.
No,
right?
no. This is not okay. You see, I can show you. Okay, this case this is the second rank, so you are replacing the Cepheids with Miras.
Yeah, but that is fine. That is not. I mean, look at the error.
So
bars.
you have
really
this one. You are
concept.
replacing the Cepheids with TRGB. In this one, you don't have any distance ladder at all. In this one, I put Cepheids and TRGB because they are compatible. They are, if you can, they are measured independently. They are compatible. So both of them are giving the same results.
So
okay?
if I don't use Cepheids,
if you don't use Cepheids at all, you have exactly the same plot. The problem,
I don't think so.
Yes, the problem, the difference is not how between Cepheid and TRGB, but how they are considering the supernovae data. Okay, so the TRGB group from Friedman is using the supernovae
You're
data in a
claiming that
different
if I
way.
do not calibrate with Cepheids,
Yeah,
I still get some value that is consistent
absolutely.
and
Yes.
in a strong tension with Planck.
Yes.
I really want to see that.
Yes, I can show. I can send you all the reference.
Yeah,
Yes.
please do.
That's true.
Thank you.
That's absolutely true.
Eleonora, I think there is a misunderstanding of what do you call solving a problem. I mean, aside from this, which I think many people agree with Yashar, on solving the problem, I mean, shifting from 67.5 to close to 69 with a larger over is exactly what I said in my talk.
No.
Inflating,
For me, solving the problem is having 73, and
so you're calling it solving a problem?
I
It's a
think
Cosmo
that
meeting, right?
we didn't solve the problem at all. There is no model that can solve the
Your
problem.
slides were showing. Can you show some of your slides on your late dark energy models?
Exactly. So
Can you show?
I'm arguing that none of the models that have been proposed until now can solve the tension. Yeah, I'm saying that these are alleviating the model. Okay, they are going in the right direction, but there is no model that is solving the tension.
But you were
Which
showing.
which one?
Just go back. Yeah, can you see? Can solve the AC tension, right? I mean,
71. Yes.
or I mean, that one is ACT plus Planck without supernova and BAO. We do cosmology.
No.
Right?
This is this is without.
Can you go some of them which has a supernova and BAO together?
I don't have here for this model.
Well, you have just
No, for this model I don't have it.
You just had it.
Yeah, for this model I don't have BO and supernovae together.
No, there was another one. Yes, wait, don't pass quickly.
This one.
No, previous one.
Okay. There are no supernovae here.
Okay, you know, this is again BAO. Can you show one of them which has a supernova?
I don't have the plot with the supernovae, but it is in the paper.
Well, if you include supernova, then you cannot solve the tensions.
You can no, I agree perfectly with you. That this is what I'm arguing as well. Okay, you can't solve the tension. You can alleviate the tension. What?
You're right.
Because this is with BAO. Okay, for BAO, the 2D BAO in this case. Okay, you alleviate the tension. Okay, but in this case, you alleviate the tension at the level of 2 sigma.
So what I'm saying is that there are many people in this room that may take all these words very seriously. When you say solve, means solve.
No, I showing here. Okay,
Right,
this is what I think. That none of the models can solve the tension. Not at all. Okay, there is no model at all that can solve the tension. No early solutions, no late time solutions. Okay. So these are just examples to show the different problems that
we have another question. Oh well, okay. Let's go on then.
Thanks for the talk. So I have a very basic question. So did you, here I am.
Okay, sorry.
Did you constrain the Hubble tension from any power spectral data? So if so, well, what kind of data you used, like any shear or convergence?
Which kind of, I didn't understand which tick you are, so what you're referring to?
You showed some, some constraint plots
Yes.
of H naught. So did you constrain the H naught parameter from any power spectra data? If so, did you use shear or convergence?
Okay.
Like what kind of?
As I said before, okay, I'm not solving the tension. Okay, all these models that I'm talking about are examples, okay, to show which are the problems that we have. So when we try early solutions, we have a problem with S8. When we are in the late time solutions, we have problem with BAO, we have fake detections, we can have negative dark energy. Okay, so this is just a summary of what has been proposed. What regarding my models here, yes, here we are always using Planck, the full temperature and polarization power spectrum. If I say we had the prior on H naught, we are using the Gaussian prior on the value of H naught. If there are the BAO data, these are available BAO data like BOS and EBOS that you can find in the literature. Okay, this is, and you have the different additional constraints.
Okay.
Okay.
Hello. Hi, Eleonora. Thank you very much for a roller coaster talk. I have two little small questions. One is your omnipotent dark energy.
Yeah.
You said that it also corresponds with dark energy of negative energy density.
Yes.
Naively thinking, this somehow is possible to reconcile with the fact that
dark energy is supposed to be 70% of the universe content at present. You mean that in the past it was negative?
No, in past was negative, yes, and now it's positive. Yeah, but again, okay, this is just an example how the late time solutions can still be a viable possibility if we have exotic cosmologies. Okay, not arguing that there is negative dark energy.
Okay, yeah, just wanted to clarify this. And the second thing was a small detail that I noticed on your transparency when you were talking about early dark energy.
Yes.
And you mentioned the oscillating model of Kamyankowski. You said somewhere that if you are oscillating in an n bigger than 5, yeah, you see, values n bigger than 5 are disfavored. Why are they disfavored?
Because there is an attractor in the radiation domination epoch, so you can't oscillate anymore.
But they are supposed to be oscillating after.
Okay, so you okay, this is
it unfreezes, it starts oscillating after equality, right?
yeah, it's just okay, it doesn't oscillate anymore if you have n larger than 5. I can send you the references.
All right.
Because of that.
Thanks.
Okay, thank you.
And to finish this session, Raul Angulo is going to be presenting talking about the backward simulation. Thanks very much. I think so. I think you're in.
Okay, yeah, as I was telling you, I'm Raul, and I'm going to tell you about how we are trying to use numerical simulations to understand better our universe and maybe chip in one of these tensions that we just heard about. And yeah, so this is the last plenary talk, and I was super excited to see all the progress, new ideas, and new theories, and also new data that was shown during the conference. And probably one thing that we can all agree with is that, still lambda CDM is our preferred model for the universe, which is somewhat surprising. I remember one of my first conferences 15 years ago, pre-Planck, pre-Bose, people were always saying, hey, with this new data, things will change, right? For sure, we're going to find something unexpected. And of course, there are these tensions that we just heard about, but overall, lambda CDM remains as the best description of our universe, which is surprising to me, not only because the data improves so much, but because we have been testing the lambda CDM model in so many different ways, right? It's not only about CMB, supernovae, but it's about gravitational redshift, it's about kinetic SC, it's about strong lenses. Anything we have tried to test the model with has turned out that lambda CDM was the best description, which could have been, now the universe could have been way weirder, right? So, of course, this is nice in one sense that we understand all these observables, but it's unsatisfying, right? Because we don't know really what the correct law of gravity is on large scales, or the nature of dark matter. Could it be neutralinos? Could it be stellar neutrinos? Could be an axion? We don't know the properties of this potential new particle, and the same with dark energy or the properties of the inflationary phase. Right, so we ask here about all these tensions, which maybe start to show us a hint of what could be the replacement or the extension of lambda CDM. But the underlying question is, are these tensions telling you something fundamental about the universe, or they're simply telling you an error that you made, a systematic error in your data, right? Or, as I want to emphasize, an error in your modeling. And how would you know, right, that your model for all these complicated physics in the universe is correct, or maybe it's not, and is making you think that there is actually tensions, right? Of course, one way to deal with this is to try to get more data, and that has been motivating all these new, dozens of new surveys around the world. And all these surveys, for instance, Euclid that was launched a few weeks ago would be amazing. And the amount and the quality of the data that will come will be really, really much better than anything we have so far. But also a key issue of this new data is that it's going to be changing in not only in the quantity and quality, but also in the nature of the data, right? So now we're going to be sampling and measuring the universe in a multi-wavelength manner, not only measuring the position of galaxies, but also of dark matter, of gas. So many of the surveys will focus on different strategies, but when you put them all together, they're going to deliver this three-dimensional distribution of view of the universe in terms of the distribution of matter, galaxies, and gas, which is going to be something unique we haven't had so far until now. Right, so that poses the question, okay, what we are going to do with this data in order to understand better whether the H-naught tension is real or not. So there is kind of this wish list for model builders, right, for observational cosmologists, which would be like how we are going to extract most of the information from this data. And for that, we would like to model very accurately what we are going to see, how the different ingredients, neutrinos, curvature, and so on, affect those observables. We would like to include small scales. We heard from Paco this morning that if we are able to go to smaller scales, we potentially can recover much more information about the universe. We would like to understand also the role of galaxy formation and baryonic physics and how we can marginalize over those effects. And crucially, also would like predictions for self-consistent predictions for all these different aspects of the universe. And all in that way, we will be able to exploit jointly all these data sets. Okay, so but no matter whether you use graph neural networks or correlation functions or field level, at the end, all these, the main problem in my point of view is that how we are actually going to be able to make predictions that we can trust for the universe, right? And it's not an easy question because the physics that's involved to make those predictions is actually quite complex. For instance, if we look at the CMB, those are relatively, well understood physics. We can predict very accurately with perturbation theory what the observable should be, and I think it's one of the reasons why CMB is so successful and also have so much impact in cosmology, because you have this exquisite measurement, but also you had a very, very robust theory that allows you to use all this data. But when we go to the late-time universe, things become way messier, right? Gravity mixes the scales, creates all these nonlinear objects, and they're super hard to describe. And of course, then we observe galaxies and gas, right? And that depends not only on gravity and GR, but also depends on the physics of galaxy formation and a lot of complicated physics, right? So this puts a lot of problems and that you can that actually are limiting the way in which you analyze current data, right? So all these issues of galaxy bias, intrinsic alignments, and so on are making us stop using a lot of the data that's already here, right? So at the moment, data is much better than theory for large-scale structure, right? So the observations are way ahead of what we can predict. So what do we do? Okay, so we need to develop a model that predicts the universe in a robust manner. So the traditional way to do this is with perturbation theory. Okay, so it's a very beautiful approach to large-scale structure, and it's somewhat simple. You can think of it. So the overdensity of galaxies or gas and so on a given scale, we know that should depend only on potentials or velocities and densities. And on large enough scales, we can expand perturbatively this function, right? So for instance, this expansion would be to have like some coefficient times the density field, another coefficient times density field square, and so on. So the beauty of this approach is that at a given order, we know the possible functions that can appear here. right? So we know that can be a delta and a delta square, but we know that it cannot be a square root of delta, right? Cannot be a sine of delta, right? So in that sense, it's a complete model for how galaxies and dark matter trace the universe, right? That only relies on certain symmetries being fulfilled, like translational invariance and rotational invariance and things like that. Yeah, so this is great, right? So in this case, we wrote it in Lagrangian coordinates, kind of very early in the universe, and then we use also perturbation theory to show how that overdensity of galaxies or gases can appear at redshift 0, say. Okay, so this is how most of the large-scale structure clustering surveys have been analyzed so far, which is great. We have also seen a lot of progress recently in terms of effective field theories, for instance. But the big problem of this approach is that it works only on large scales, right? So we are giving up on a lot of information. Also, it's not easy to extend this approach to cross correlations, for instance, SC with lensing and so on. And also, if you want to apply nonlinear or non-trivial statistics, counts in cells, in consequence functions, wavelength transforms, it's also, this perturbation theory does not give you a way to deal with those statistics. So we're giving up on, we have a good theory to describe the universe, but the price that we pay is very high. So what is the answer? Do we give up on the small scales? Yeah, that price is very high. I just give you an example. For instance, we're interested in neutrino masses. So these are comparing how well you can constrain neutrino masses as a function of the small scale of the scale that you include in your analysis. So if you use kind of linear theory, you get this. It's normalized to linear theories is 1. So if you are able to go to twice smaller scales, roughly the scales where perturbation theory breaks, your improvement is a factor of a few. But if you're able to go to nonlinear scales, then you potentially 20 times stronger constraints, right? So there is merit in going to these small scales, right? So it's a big price. So what do we do, right? Okay, the obvious answer is, hey, we know perturbation theory breaks down, but we know how to simulate the universe, right? We have numerical simulations. So why don't we use them? So this is actually has several advantages. So we can write the equation of motion for particles in the universe. We know how to solve them pretty well, right? Over the last 20, 30 years of, thanks to the work of hundreds of scientists. Nowadays we know how to create numerical simulations of gravitational evolution. We understand very well the numerical errors, convergence, and so on. We can constantly testing the impact of different assumptions, and here is an example that different codes, approaches agree kind of at the percent level, right? So this is great, right? We have a numerical simulation. We have a theory now that we can use down to nonlinear scales. But of course, the elephant in the room is the modeling of baryonic physics and galaxy formation. So this is not only difficult, much more complex physics, but it's also very uncertain. So just to give you a glimpse of this, right? On large scales, we know that general relativity and gravity work, the dominant processes. But as we go to smaller scales, all the hydrodynamic forces, matter and gas accretion and cooling to halos become super important. Then on smaller scales, galaxy mergers will, and even the smaller scales, how stars form, like how the stars evolution affect each other becomes relevant. And even on the smaller scales, the accretion of gas onto supermassive black holes is crucial because they can inject energy in forms of jets that could actually change the way in which the large scale structure is distributed. Okay, so then, okay, of course, we have hydrodynamic simulations. We know roughly how to solve this, but to me, there are like outstanding questions, right, that we need to solve before we are able to use this really for constraining cosmology. So the first is that is our current understanding of how galaxies form detailed enough, right? Until 5-10 years ago, none of the hydrodynamic simulations were able to form disks, right? So are the models really complete, or are there possible physical phenomena that we are not including in our simulations? And are they actually considering all possible formulations of galaxy formation that are plausible, right? In some sense, are our galaxy formation models unique? Or are there multiple ways in which galaxies could form that could relate differently with the underlying cosmological model, right? So all these things of is it enough, it's not enough, is very hand wavy, right? I think formally what we would like to have is as a model that we can attach an uncertainty to, right? So we know that we have a model, but also we would like to know this model is 2% accurate, or is 1%, or is works well in voids, but not in clusters. So if if we have a way of modeling this theory error, we will be able to have robust constraints. So yeah, so we can say we can take the approach of camels, for instance, and vary a lot of parameters, right? That some accounts for a little bit of this problem, but doesn't solve it completely, because it still could the universe could be outside this hyperspace covered by camels, right? The physics in the universe could be different than what we assume in the hydrodynamic simulations. So, and that is it's actually a very tricky question, because we don't know how to test for this, and we don't know how to prove that we have those errors under control. So remember that we want to have a rough estimate that agrees with Planck, right? We would like to use these measurements to claim that neutrino masses are 0.03 and are inconsistent with solar and neutrino experiments. Therefore, we discover exotic neutrino physics, right? So we need to be able to handle this approach very precisely to convince ourselves, but also the broader physics community. And I wanted to give you an example of this problem. It's a paper, now it's 30 years old, written by Richard Bauer and others. Richard sadly passed away recently. So that was done in the 90s, and I really like this paper, because at that time there were measurements from the APM survey, and so it was the clustering of these galaxies. And the favorite model at that point, that was the standard cold dark matter, did not fit the data, right? So people actually started speculating, if you use a lambda with 0.7, actually it does fit the data, right? So, but what these guys did say, okay, what about if galaxy formation is more complex than what we thought? So they came up with this cooperative galaxy formation model, in which the probability of a galaxy forming on a given position in space was also a function of what happened on a different scale. So they did not make a specific reference to a given physical process, but you can imagine that UV background could be responsible. For instance, if you have a nearby quasar that emits a lot of UV photons, that's going to dissociate atoms in your galaxy and make stars form less efficiently. Or maybe there's galactic winds, right? That were ejected from a different galaxy. Right, so they came up with this model, and actually then they could fit perfectly the data, right? With the standard cold dark matter model, right? With no dark energy. Actually, it's funny, because the final conclusion of the paper is that the best test of the CDM model remains those are sensitive to the mass rather than to the distribution of galaxies, right? So these people are saying, forget about galaxies. We cannot use galaxies, because we don't know about all this physics, right? How can you then claim something fundamental of the universe if you don't understand galactic winds? Of course, this was a very, very extreme model, but we have similar analogous problems nowadays, because we also care about much smaller deviations, like the effect of neutrinos of the order of 1%. So another example, for instance, is how the physics of galaxy formation affects, it's going to affect Euclid, for instance, right? So you could imagine that Euclid is going to detect galaxies that have strong emission lines. The emission lines are related to the amount of stars that are formed. And now you imagine that you have a galaxy that falls into a larger halo, because of ramp pressure, all the cold gas of that galaxy is going to be stripped away, and very quickly they're going to stop forming stars, right? So then you will not see them in Euclid. So, and of course, that has implication for how the spatial distribution of these galaxies. So the question is, how much do we trust the treatment of ramp pressure in semi-analytics or in hydro simulation, which depends very in a lot of detail about the internal distribution of galaxies and the interaction of the intercluster medium, all this hot gas, with the gas that is inside galaxies. So yeah, maybe still we have to focus only on the distribution of matter, as Richard pointed out. But also now we know that that's also not possible, right? So we know that all these hydrodynamic processes and galaxy formation does change the distribution of matter, right? And this is how much it changes the distribution of matter as predicted by various hydrodynamic simulations. So some of them they tell you no, matter will be clumpier. Others will tell you no, matter will be smoother, and we don't know which one is correct. If any, maybe none of them are correct, right? So what? I mean, so far it's been a bit depressing what the message, but what do we do? Do we give up simulations and the modeling of galaxy for cosmology? Do we remain only with perturbation theory and very large scales? So the first answer is that we cannot afford it, right? If we do that, maybe for the current generation of surveys, we don't lose so much, for instance, for DS. If we do it for Euclid, that's going to be a disaster, right? The cosmological constraints that you would derive are factor of 10 worse than the forecast. So we cannot afford it. But also I think that we should not be overconfident in the way we model the universe, but also we have a few examples where we can gain physical insight from comparing data and simulations, keeping in mind also all these limitations, right? And those examples are, for instance, Lyman alpha forest, or all the whole gravitational lensing and cluster cosmology communities rely on numerical simulations, right? But if we rely only on a single probe, then we can only put a lower limit to the theory error, right? We can only say my error is at least as large as what these hydrodynamic simulations tell us, but could be unbound, but it could be arbitrarily large. But all this new generation of data and service actually give us maybe a way around this, right? Which is that if we consider many different views of the universe and we develop consistent models for it, then we can, if all these observables point to the same direction, maybe we grow a bit on confidence of that this is the right model. Again, as an example is neutrino mass. If neutrino mass shows up in clusters, in voids, in SC, in CMB lensing, maybe then, even though all of them will have their own errors, maybe we can trust a bit more. This is a bit of leap of faith, and some people still might criticize this and say, no, still you cannot do that. But in this context, I like a sentence that was in a letter that Milgram sent to Bacall in the 80s at the Institute for Advanced Studies when they were discussing about MOND, right? So Milgram was telling, hey, look at these rotation curves of galaxies. So clearly GR is wrong. And Bacall told him, hey, don't worry. I think the data is messy. Wait a bit more. Then when we have really good data, we will see, right? Let the dust settle, and then you will see the truth. And Milgram replied, if you wait for the dust to settle, then you will be there to see the truth together with everybody else, right? So I like a lot this, and yeah, so we don't want for the dust to settle, right? We want to take a bold approach and let's try to go and model the universe in a way that we can simultaneously exploit all these surveys. And that is actually the motivation behind this Baku project that I've been working on together with a lot of people, some of them who are here, Giovanni, Sara, Lourdes, and Matteo, in San Sebastian, right? This beautiful city in the northern part of Spain. Right, so our overall approach is let's try to build models that are as accurate as possible for the universe, but also that are flexible enough, right? So that we can have effective descriptions of the relevant physics, which we can then fit and describe all the possible plausible galaxy formation models, and try to not use hydrodynamic simulations to analyze the data, but to use them to learn about what the relevant physical processes are, and then let the data, the large-scale structure data, to tell us which model, which astrophysical model is the correct one. And then hopefully when we do that, we can constrain cosmology after marginalizing over this uncertain galaxy formation. So I will spare you the details of how we do that, but in a nutshell, the basic idea is that for a given cosmological model, we can use numerical simulations to describe the dark matter. Then we have models for the distribution of galaxies and gas in those simulations, and then we can vary all the parameters that could regulate star formation, tidal stripping of stars, and so on, to create three-dimensional universes. And then you can actually compare directly with the data, applying the same analysis software, and then derive cosmological constraints. Yes, I was telling you, I will spare you a lot of the details of how we do that. Just to mention that there was a lot of work behind understanding the mapping between cosmology and dark matter, run these huge simulations in large supercomputer centers, dealing with petabytes of data, how we can reliably predict all this nonlinear structure, and also use machine learning to speed up a lot of this process, and mixing also perturbation theory with numerical approaches. So I wanted to show how one of our simulations look like. We are flying through the okay. Okay. Okay, well, I will leave the link there. But yeah, actually, we have this this video in YouTube that is in virtual reality. So if you have Oculus Googles, then you can actually move around and then experience the universe like as flying through. Yeah, but as you can see, all these simulations resolve the very detailed structure of dark matter with very, very high precision on super large volumes, right? Just to give you an idea, the resolution of these simulations are about 1,000 times larger than those of Quixote, and the volumes are also hundreds of thousands of times larger than camels. So this allows us to really sample the very, very large scale distribution of dark matter with super high accuracy. Yeah, we have also developed many tools so we can reuse the simulation, so we can very quickly vary the cosmological parameters that these simulations represent. So this allows us to test the impact of, again, neutrinos, curvature, and so on. Okay, so. Okay. Okay, so this was dark matter. How do we deal with gas? So this was PhD thesis of Giovanni, and the basic idea is to also try to take unbody simulations and try to describe models or create models for the role of astrophysics, star formation, and so on. So the way in which we do that is to take like a dark matter halo, and we perturb the positions of particles so that they represent different physical processes. For instance, this gas ejected. So we take a fraction of the mass and we can eject it outside the halo, right? So the amount of gas and how far this gas is expelled to are free parameters of the model, right? So we have like an effective description that then we have tested it in many different ways. Particularly, we compared it against hundreds of different hydro simulations, and we show that it's always a good description of the underlying physics. So this again give us the opportunity to then apply this not to a hydro simulation but to the real universe and infer how much gas has been effectively expelled by whatever process, without making a specific reference to the process or without relying on the correctness of any specific hydro simulation. We adopt a similar approach for how galaxies will populate the dark matter universes. And this is a work done by Sergio Contreras and Sara Ortega, who gave a talk yesterday about the specificities of the way in which we model the star formation rate of galaxies. But in a nutshell, what we do is just connecting the positions and histories of individual dark matter structures, subhalos in our simulations with galaxies. And we have models for star formation rate, how efficient are these tidal disruptions or the stripping of stars. And those, again, are parameters that we vary freely, and then we try to fit with observations. I have another video of showing you how this, like now it's a fly through one of these universes. Before I was showing you the dark matter. Now I tell you what the distribution of galaxies look like in one of these models. Now you can see that we have all the small scale structure, and here's a big cluster with galaxies potentially with different colors and stellar masses and so on. And yeah, one of the cool things that we can do is that we we have created tens of thousands of variations of this particular model, right? And each of them could correlate differently with the underlying dark matter, which in turn depends on cosmological parameters, right? Which is also shown here. Okay, so that was the optimistic approach, but still you could argue back, hey, Raul, you spend a lot of time arguing that, we don't know how we're going to convince other people that your model is complete, right? I mean, surely these kind of more flexible models I would personally trust them more than a specific galaxy formation model, but still they suffer the same thing, right? How do you know that there might be this cooperative galaxy formation that you did not take into account, right? So we are in parallel, we are developing an alternative approach, which is, if you remember this perturbative description of galaxy clustering, that is, this is one loop well, anyway, so this works nicely, does not rely on a specific astrophysics. And this, in this case, is written in Lagrangian space, and then we have to move to Eulerian space, right? Redshift 0, 1, whatever, and then to redshift space, right? Okay, so what people normally do is take this expression and then use again other flavors of perturbation theory to do this advection. But what we realize is that this mapping between Lagrangian and Eulerian space is exactly what embodied simulations solve, right? They tell you how a given particle at redshift 100 or so moves and ends up in redshift 0, and what is the nonlinear velocity field. So that is so the idea of these hybrid bias expansions is to replace part of this perturbative approach, the part that we know how to do with simulation, which is this displacement field, and drop the perturbative side of that and replace it directly by numerical simulations. This actually works surprisingly well. So it's something relatively simple, but we have shown that it extends a lot the range of validity of perturbation theory. Crucially, here we cannot only predict correlators like correlation functions, power spectra, but we have directly 3D realizations of these hybrid models, and this comparison of what are the distribution of galaxies in one of these more physical models and what this hybrid bias expansion predicts. And well, you can see the similarities in terms of properties of voids, filaments, clusters, and so on. Recently, Francisco Mayon have extended all these ideas to intrinsic alignments, which is a big systematic or big showstopper for weak lensing. So now we have applied the same ideas to that problem. So again, it improves a lot of what we can do with these agnostic approaches. And we have also coupled it with some field level emulator, so we can also create many of these realizations in our work with Drew Jamison, who's also here. Okay, so at the moment, everything had been a bit qualitative. I wanted to show you a few more quantitative plots. This is how well we can predict the nonlinear matter power spectrum with our approach as a function of scale. So the accuracy is about 1% up to k of 1 and about 2% up to k of 2. So very quickly, in a matter of microseconds, we can create this nowadays. This is how well we can represent the effects of baryons. So 1 means the baryons don't do anything. Below 1 means baryons do suppress the clustering. And these symbols are predictions from different hydrodynamic simulations. And our empirical model is this dash and solid lines. You see that no matter whether you think Eagle has the right physics or Bahamas, this is contained within our approach. And what about galaxy clustering? So this is the multiples of the power spectrum in redshift space for something like BOSS, state-of-the-art galaxy surveys. So again, symbols are the data, lines are our description. So perturbation theory breaks up to here, and now we see that we have a statistically compatible description of galaxy clustering all the way to the scales 3 times smaller, so potentially 27 times more Fourier modes. Okay, so So we have done that. So now I wanted to show you a couple of applications where this, I think, is making a difference. So the first one is addressing the SA tension. So another work led by Giovanni. So the Dark Energy survey is great. They have done an amazing job. But one of the things that they had to do was to not use many of their data points, roughly half of them, which is shown here. These are the shear correlation functions, a fraction of them. And all the shaded area are the data points that they could not use for their analysis because of issues of baryons, intrinsic alignments, and the accuracy of the nonlinear power spectrum. So we use all of our approach to reanalyze all this data, including now essentially the full data vector. And here are the results. So when we use all the scales but neglect the role of baryons, we get like a 2 sigma tension with Planck in terms of S8. This is the famous S8 tension. But when we include baryons, with their tension is essentially gone, right? So now they are compatible at less than 1 sigma. And actually, we're happy that after our paper, there was a more like official reanalysis of DES and kits, and they agree with our conclusions. So it seems like the evidence for the S8 tension in lensing is at least weakened, I would say. But one of the cool things of our approach is that not only measure cosmology, but also we can measure astrophysics, right? We can do astrophysics, cosmology marginalizing over astrophysics, or astrophysics marginalizing over cosmology. And this is the famous power spectrum suppression plot of the role of baryons. Again, this is what is predicted by various simulations. And now we can overplot what actually the data is telling us, right? And this is the shaded area. So it's telling us that Eagle and Illustris are not compatible with the data, and it's something more like the Bahamas, a different simulation is more compatible. Another cool thing of these physical models is that not only tells you, what the impact for your statistic is, but make predictions for something else. And in this case, are predictions for the gas fraction in clusters, how much gas clusters of different mass have retained. And our predictions, I mean, what the data, the lensing data tells us this value is shown here in the dash, in the shaded region, and direct measurements from X-ray and other approaches are shown in symbols. So seems to be that our approach applied to lensing gives you consistent results with direct measurements of lensing. Sorry, Other problem is that we have addressed is the so-called lensing slow. This was an issue identified by Alexis Leto 5 years ago, and then confirmed by many papers afterwards. And what she did was to take both galaxies, measure the clustering, and use one of the traditional models to predict kind of predict what would be the average halo mass around these galaxies, and therefore predict how much lensing these galaxies should cause. And then you can go and measure the shape of galaxies around these both galaxies and what's called galaxy-galaxy lensing, and compare your predictions or your expectations from clustering with the actual predictions. And then she found that, this is what is shown here in this ratio, that the measurements are about 30% lower than what you would have expected. Therefore, lensing is low. So people have used this measurement to argue that maybe there's this evidence for new physics, and maybe it's another phase of the SA tension, and so on, right? So what we did with CONAS was to try to investigate this problem now with these much more sophisticated models, and actually we found out that this actually expected. There's no really reason to find to believe that this has to be beyond lambda CDM model. And this apparent tension is just caused by physics that was neglected in these models. One of them is the role of baryons. People usually neglect those. Now we know that from the previous slides, I was telling you how baryons can actually affect the distribution of matter around galaxies. But there are also other things like how the properties of galaxies correlate with the properties of halos and triaxialities of halos and so on. Right? So it's just another example that sometimes when you have the wrong model and apply it blindly without regarding the actual accuracy of the model, it can make you believe that things that are not really there, right? And might be confused with new physics. And the final example is I wanted to give you is this with our empirical galaxy formation model. what we can do is to vary for instance, how strong tidal stripping is of stars in clusters. So if we think that tidal fields are very strong and it's going to strip a lot of stars, those galaxies very quickly will lose a lot of luminosity and will not be detected. So if you plot their clustering, so on small scales, the stronger the stripping, the lower the amplitude of the correlation function. This is what is shown here. This is the blue is a very strong one, red is a very weak one. So we see that all these small scales that could potentially be used for cosmology in reality is actually super dependent on assuming that you have the correct tidal stripping. So what we did, we took the largest high resolution simulation in the world, is Millennium TNG done by Volker Springel at MPA. And we created mock catalogs and of different number densities. We also have versions with 5 different flavors of semi-analytic galaxy formation models on the same simulation. And we saw whether our model was able to reproduce all of them and whether it was able to correctly infer the cosmology of the Millennium TNG. So the answer was yes, right? So now we vary astrophysical parameters and cosmological parameters. And now we have these 4 different flavors of galaxy formation. All of them, for instance, prefer very different tidal stripping and merger timescales. This is shown here, right? So all the posteriors are all over the place. They are different galaxy formation models. But when you focus on cosmology, this sigma 8 omega matter, they're all consistent with each other and consistent with the true underlying cosmology of the simulation. So this give us a lot of, give us more, a little bit more confidence that this might be something worth pursuing. Okay, so these are my conclusions. So the first thing is that modeling the universe is hard, especially in the future will be even harder when all these future surveys are going to focus on different galaxy populations. We not only care about correlation functions, we care about all these complex nonlinear transformations of the density field, complex summary statistics. But we shouldn't give up, right? But I think this gives us really an opportunity to develop jointly galaxy formation and cosmology and learn hopefully about both of them. And and even though galaxy formation is still uncertain, I think we do have a good understanding. We have progressed a lot about our understanding of galaxies, and we should use that information to improve our constraints on cosmology. And as the galaxy formation field evolves, I think that should feed back into cosmological community to deliver stronger and stronger constraints and more robust ones. And I think developing jointly galaxy formation and with these effective models, I think is the only way to really have a maximize the amount of robust information that we can extract from all these amazing data sets that will come up. But we shouldn't be overconfident, and I think this is something that we have to constantly be self-critical about. But yeah, I think it will be interesting couple of years lying ahead. And the final advertisement, we have many of these things that we have developed here. We have in terms of emulators, neural networks that are pre-trained that you can access and use them for your own research. And yeah, so I think we're also a very open group of people. So if you are interested in these topics and would like to help us in our in developing further these ideas, please contact us, and we're happy to work together. So thanks a lot.
Many thanks, Raul. We have time for questions.
Hi, thank you very much. Could you tell us a little bit more about the intrinsic alignment modeling?
Yeah. Did I put slides? No. Yeah. So essentially, intrinsic alignment is you would like to know in the so whether the shapes of galaxies are correlated with each other, right? And how those correlations depend on galaxy formation and so on. So yeah, so the way one can do is in analogy to this perturbative galaxy bias expansion, is to say that the shape of galaxies are given by derivatives of the gravitational potential. That's the most general thing you can do. And then you can see what are the possible operators of the gravitational potential that can appear to a given order, right? So you might be familiar with NLA or TAT. These are essentially, they do essentially the same thing, or more recent versions of effective field theory for intrinsic alignments. So in this approach, we write down the problem in exactly the same way, but we write for these for shapes in Lagrangian space, how the shapes were, you imagine, at very high redshift, and then how those shapes appear at redshift 1 would depend on these alignments at redshift, say, 100 or so, and of the displacement of these galaxies. So those displacements are the ones that we extract from numerical simulations. So we have in the paper, we compare against these models, the TAT and others, and yeah, we showed that it increases a lot the range in which these models can describe all the shapes of halos and galaxies. And so it seems with less free parameters than TAT, we can model things down to smaller scales. So.
Can you kind of model the intrinsic alignment based on type of galaxy within this formalism or not?
So the beauty of this is that this works for any type of galaxy, right? You don't need to make a different model for blue or red galaxies. So they will just have different values for the free parameters of the model, which are these bias coefficients.
How many free parameters do you know?
So we have 5. Yeah, but we have we have reduced versions that might, yeah, but yeah.
Thank you.
Oh, thank you for the nice talk. I have a question. Have you checked a hybrid bias expansion on probes where you simultaneously probe like the matter and the galaxy? So something like lensing and clustering?
Yeah, so we have we have done only clustering and also simultaneously galaxy-galaxy clustering and galaxy matter cross correlations. Yeah, and yeah, seems to work up to K of 0.6 or so. Yeah.
Thank you.
So everything you said about these, like the uncertainty on the astrophysics is of course entirely correct, but I would say it also applies to these extensions to lambda CDM, that if lambda CDM is not the entirely correct cosmological model, we have all this uncertainty with our dark energy models, dark matter models, and other extensions, to which I think you showed you had some of these extension parameters. To which extent do you also include these in these analyses?
Yeah. So all the framework I presented was developed within lambda CDM plus dynamical dark energy, W0 and WA, and massive neutrinos. But in principle, it can be extended to an arbitrary number of lambda CDM extensions. But yeah, I mean, I agree that that there is this issue of model misspecification, right? So if your model is not correct, it's very hard to infer something about the model itself. The difference between astrophysics and cosmology, in my point of view, is that we do care about lambda CDM not being the right one, right? So we want to know, hey, the model doesn't fit, right? That is actually a discovery per se. But a discovery that our galaxy formation model is not good enough, we already know that, right? So in that sense, formally, they're both at the same, they represent the same problem, but I think it's, in practice, I think they are in different kind of levels. And yeah. And also, I think we hope to improve our knowledge of galaxy formation, constantly, right? So hopefully that error decreases.
Is there a final question? Over there? Yeah.
Thank you. Very nice talk. So about this hybrid bias expansion, so you go to like K of 0.6 and so on. And so we know that there are higher order bias terms that are not valid at those. I mean, they can be bigger, much bigger than the ones that you have here. And then the fact that you're going with the nonlinear displacement, I guess, helps. But do you understand really what is happening? Why are you able to go to 0.7 while with EFT we go to 0.5? I mean, what's happening there?
Yeah. So I think it's a mixture of things. One is that even though formally, higher order bias B3, B4, so could be very large. for the typical galaxies samples that Euclid or DESI will observe, these B3 are very, very close to zero. So the third order contributions to the bias expansions are seen as subdominant to the third order contributions to the displacement field or to the velocity field. So I think that is one thing that essentially that the terms that one neglects in the bias expansion are the dominance are subdominant compared to the errors that of the same order in the displacement field. And the second thing, which I think is perhaps even more crucially, is the role of velocity fields, right? So I think even though, you know, this in real space, you might have more perturbative control. When you go to redshift space, I think there is a lot to gain from having these non-perturbative velocities, which can affect, you know, very, very large scales, right? So in other words, I think the first thing that breaks down in the standard perturbative approach are first velocity fields, which we have non-perturbatively, then displacement field, which also we don't have perturbatively, and then will appear these higher order terms in the bias expansion.
Okay, thank you very much. I think let's all thank Raul and all the rest of the speakers. I'm now going to pass the microphone to some of the organizers for final announcements.
Thank you. Thank you, David. Just very quickly, a few acknowledgements. So first of all, I would ask you to please thank all the chairs of all the sessions. And then we have many, many people to thank, but we single out 3 people that did a lot of work. First of all, Monica, who's right there, and we ask her to come downstairs. Please, Monica. There she is. And so we really thought we had to buy flowers for all the work. Thank you, Mike, again. And also, I hope they're not hiding. They're trying to hide centrally, but Emilio and Antonio should also come downstairs and be thanked. And you will notice the difference. Emilio, you have to come downstairs, yes? And Antonio as well. You notice a different kind of gift that we have. So we have a money ibérico for Emilio, of course. And a classic chocolate for Antonio. Thank you, Antonio. I'll give you one.
Thank you very much, Matteo. Well, you've noticed I lost my voice. So it's a great pleasure to finish this conference, which I think it has been, at least to me, very happy about it, with Leszek Roszkowski, as I described yesterday, for those of you that were at the dinner 3 times. He's the founder of this series. It's the 26th. Long series, and he has a lot of statistics, a different view. Okay, thank you, Kirsten, for telling me. So he has a special view of all these conferences. So he's going to give, well, some perspective on what these Cosmo meetings are. So please thank Leszek for having initiated this fantastic series.
Yeah. All right. So what can I say? This will not be a summary talk in any sense. Just a few remarks at the end. And I've not lost my voice yet, although I'm on the way to to have it for this to happen. So let me just share with you a few points about Cosmo meetings. It all started from very humble beginnings back in 1997 in Ambleside, in the Lake District, the beautiful Lake District north of Lancaster, where I was at that time in Lancaster, a new faculty member. And somebody suggested, why don't you organize, maybe some workshop, something, you are new, maybe, it would be a way of getting introduced yourself to the department. And the guy was from the United States, and he wanted to come and visit the Lake District of this event. So I took it seriously, and I decided to do it, and I invited everybody that I knew, including Stephen Hawking, Rocky Kolb, Andre Linde, Graham Ross, all those big shots from John Ellis from that time, and they all came, including even Juan. So he was here, and he was at that meeting, and the meeting was honestly such a big success, and it was so much fun that we decided to carry it every year. So the meeting started traveling around the world. Annually, and truly around the world, as you can see, Europe, the United States, and then Asia, Japan, China, Korea first. So it started really going very well. And today this week we are celebrating the 25th, 6th Cosmo. Should have been the 27th, but one Cosmo was missed because of the COVID pandemic. It was supposed to be done in Rio in 2020, but it was called off because of that. And we thought about doing it online, but visiting Rio and Brazil online is not that much fun. So this year we are having Cosmo in Madrid, and I thought this would be the time to do the thanks, but this has been already done, so what can I do? I think I just invite you to do it yet again. Let's thank the organizing committee and the secretarial support for their hard work. All right. I have no bouquet of flowers, unfortunately, unless you bring it back and I give it. All right, so the meeting has been organized by all those people whose names you can probably not read, because I would have a hard time reading them, but you've already seen them, and they've done a great job. And that's why I saw all the speakers. So thanks to all the speakers again. We should also thank all the speakers, because I think that, including yourselves, right? Because you've really done a fantastic job. Let's look at some numbers again as well, which is this is one of the larger Cosmo meetings. 277 participants, excluding locals, I understand. So that goes over 300, I would suppose. That's one of the bigger ones. So there were meetings at CERN, in Chicago, which are obviously sort of big places with the local community, which were reaching over 300 people. So this is one of the larger ones. That's really good. That's really very encouraging. And obviously, unsurprisingly from Europe, the number is the largest, nearly 200 people. From North America, 30, South America, 7. I think this includes Central America. Asia, 35, which is, I would say, somewhat on the slightly lower side, because usually the Japanese contingent comes, big. And I think also here there are many Japanese people. From Africa and Oceania, there are also a few people. Now, we have also a breakdown for male versus female, a gender breakdown, and it's quite impressive, right? Because you have about 3 to 1. Last year it was 4 to 1, and it's, I think, quite good, really, comparing other fields and other sort of domains of physics. So I think this community is getting more balanced in this respect. Now, while it is getting more balanced in this respect, it's getting completely unbalanced in the age profile. some more senior people around us, including myself, noticed that this community is getting increasingly younger. I don't know what to do about it. Anyway, so this is the kind of series of meetings that's been running on for so long, and you may wonder, self-perpetuating series of meetings. Well, yes, but also there is a body behind it, a steering committee, a bunch of people who want to make sure that those meetings are a success. And they basically consist of some of the people from the first meeting and then the chairs of the subsequent meetings. And so the list is growing and is becoming a bit too big. But next year you will see the name of Juan also on it, because he's been chairing this meeting. Some people have left us. My good friend Stavros Katsanievas. Some people stepped down. David Colbert also died. Lev Kaufman died. Some people have left the meeting, the retired and just left. Right now, what is the role of the steering committee? We sort of try to keep our hands off particular meetings. This is in the hands of the local organizing committees and scientific committee. So we don't do that. We just want to make sure that where the meeting goes, it will have some impact on the local community that will basically, help grow the local community. And it's very important for us to make sure that the local community, sort of does it and profits from it somehow. So we're quite impressed, for example, that in the case of Madrid, we found out they actually started running business. It seems money is important, right? I looked more closely, actually. This is done by Miguel Sanchez, also known as Miguel Sanchez Conde, by some, and since years ago it is. So this is something that certainly convinced me that Madrid should be the host of this meeting. It's not something that only happened here in Madrid. For example, last year, another Miguel Curtin started a real business, with solar panels to generate more money for the community. Well, not only that, he also generated some other business like this, in fashion and this. So this is something that really impresses us, when people do things like that, because we know that they take their job seriously. Right. Okay. So Cosmo, being already so many years, after it started having grew up its own traditions. So one tradition that we had from the very beginning, that there is usually no summary talk. So this is also not a summary talk, just concluding remarks. And then another tradition that we've grown up with is that, and this is a very important tradition, that at every meeting there should be some rain. There we had some concern, because while at the first Cosmo meeting we had plenty of rain, 2.5 days it rained forever, until it stopped just less than an hour before an excursion. It was beautiful, and it was beautiful for the rest of the conference and beyond. Then there is a tradition that each meeting is different, which is a nice tradition, because that means that the meeting is really vibrant, is lively, it addresses different points. And then there are also, of course, some common themes, because it's Cosmo. But then there is another tradition that started growing more recently, is that, at least from our perspective, the participants are getting increasingly younger, as I mentioned already. In fact, I realized that there are some participants here who are younger than the Cosmo. I'm serious. So yeah, well, there's not much we can do about it. In fact, I think I'm quite happy with it, to be honest. Now, there are trends and perspectives also that are worth sort of keeping in mind, realizing, as Juan mentioned. So on today's Cosmo menu, we have things sort of fairly random. It's not exhaustive list. That I put here, power spectrum, nucleosynthesis, early universe, all those things. dark Hubble constant and extension, dark matter neutrinos, gravitational waves, primordial black holes. Now, for those younger ones, means most of you, let me remind you that, for example, at the first Cosmo meeting, some of those subjects didn't even exist, were not even mentioned. There was no talk about gravitational waves whatsoever. There was nothing about primordial black holes. String cosmology, quantum cosmology, models of Big Bang, holography, all those things were basically not there. On the other hand, there was much more collider physics. Larger scale structures were starting, but what is equally important, was that the sense in the community or the communities was that particle physics and cosmology were two different communities. But there was a sense on both sides, in some sense. Tini Weltman, a Nobel Prize winner, whom I got a fortune to meet because we had fun discussions, he told me, cosmology is not science. He told me cosmology is not science. That was sort of bad for me because I had just switched from particle physics to cosmology a few years earlier. It was one of the first ones. So, well, as you can see, Nobel Prize winners can be wrong. Can be very badly wrong. For one thing, we are witnessing, and we are participating in opening new windows on the universe, right? We have CNB, of course, but then gravitational waves is opening up a new window on the universe. And then if primordial gravitational waves are measured, we have a window up down to the time of inflation. Fantastic. The 21 centimeter measurement would hopefully open up a new window. And then eventually, I believe dark matter, once it's discovered, will open up a new window on the earliest universe well beyond 1 second. So we are really witnessing new, sort of historical moments in some sense in the development of this science. Okay, so it's not supposed to be a summary talk, so I better finish. So we are here, 23, in Spain, and I've heard that there will be another year, another Cosmo meeting. So we should ask ourselves where it's going to go. Well, it's going to go to Kyoto in Japan. So I hope to see you there in Kyoto in next year. Thank you.
Thank you, Leszek. That was very nice. Well, indeed, you're all very welcome to Kyoto. I don't know whether Takahiro wants to make a few words, but he's here. He's the chair for the next one.
All right, yes. Maybe you can just come forward.
It would be a great opportunity. You want to say something? We didn't have this prepared, so if he doesn't want to, that's okay.
So I hope you've got some inspiration of what kind of business you should start in Japan earlier to have income.
Business.
They actually do already.
Okay, well,
they have a petrol station there.
Thank you all for coming. Of course, we still have some
Thanks
panel
for
sessions
coming.
in the afternoon, but a big round of applause for you. You are the future of cosmology.